The universe is full of astonishing beauty, with stars that burn brightly for billions of years, shaping the cosmos around them. But just as all things have a beginning, they also have an end. Every star, every galaxy, no matter how grand, will eventually fade, their light extinguished as they reach the end of their life cycle. These cosmic graveyards are scattered across the universe, silent witnesses to the passing of time and the inevitable decline of the stars that once illuminated the night sky. Can life survive in a universe slowly running out of energy? And what does this mean for the future of everything we know? Join us on a journey through the galactic graveyards, where the last remnants of the cosmos whisper the stories of the universe's final chapters. The birth of a star. From nebula to nuclear furnace. Stars are born in the cold, vast reaches of space, where clouds of gas and dust swirl in the darkness. These clouds, known as nebulae, can stretch across millions of light-years. Despite their seemingly tranquil appearance, these vast clouds are teeming with the potential for incredible transformation. The birth of a star begins when a portion of this cloud begins to collapse under its own gravity. As the gas and dust particles are drawn closer together, they begin to heat up, compressing more and more as time goes on. Initially, the gas is cool and diffuse, but as gravity pulls the particles closer, the material begins to pack together, causing it to heat up dramatically. This is a process known as gravitational contraction. When enough mass accumulates, the pressure at the center of the cloud becomes intense and the temperature rises to millions of degrees. The central core becomes a hot, dense region known as a protostar. This is the earliest stage of a star's life, and although it's still not a fully formed star, it's a precursor to the energetic furnace that will eventually emerge. During this stage, the protostar radiates a tremendous amount of energy, but it's not yet generating energy through fusion. The energy released is mostly a result of the gravitational contraction of the gas. At the same time, the surrounding cloud of gas and dust begins to flatten into a rotating disk. This disk is made of leftover material that hasn't yet collapsed into the protostar. Over time, this material can accumulate to form planets, moons, and other celestial bodies. As the protostar continues to heat up, it reaches a crucial turning point. The temperature and pressure at the core rise so high that nuclear fusion begins to take place. This is when hydrogen atoms, the most abundant element in the universe, are forced together to form helium, releasing an enormous amount of energy in the process. This marks the true birth of the star, as the fusion process begins to generate the energy needed to sustain the star's heat and light. At this stage, the star becomes a fully fledged nuclear furnace, capable of producing vast amounts of energy that will continue to fuel it for billions of years. For a star to reach this stage, the pressure and temperature at its core need to be incredibly high. The force of gravity pulling inward is counteracted by the energy generated by fusion, creating a delicate balance that allows the star to remain stable. This is what is known as hydrostatic equilibrium, the balancing act between the inward pull of gravity and the outward pressure from fusion. If this balance is disrupted, the star may undergo dramatic changes, but as long as it's maintained, the star will shine brightly, radiating energy into space. As the fusion process continues, the star's core becomes more stable. The outer layers of the star, still hot but not yet undergoing fusion, begin to radiate heat and light outward. These layers of gas and plasma, which are in constant motion, give the star its characteristic glow. Over time, the energy produced by fusion continues to fuel the star, and it remains in this stable state, continuing to burn hydrogen in its core for billions of years. Stars are not all born in the same way, and their final form depends on their mass. A star that is relatively small, like our Sun, will spend much of its life burning hydrogen in its core. But a star that is much larger will burn through its fuel much more quickly, reaching the stages of its life cycle more rapidly. These massive stars will end their lives in dramatic ways, either as supernovae or collapsing into black holes, while smaller stars like the Sun will gently shed their outer layers and leave behind a white dwarf. As the protostar forms, it can have a profound effect on the surrounding gas and dust. Strong winds from the protostar blow away any remaining material that hasn't yet condensed into the star, and radiation pressure pushes away the outer layers of the surrounding nebula. This process is called photoevaporation and helps clear the space around the newly born star, allowing it to shine more brightly and spread its energy outward. Once the star has reached the stage where it is burning hydrogen in its core, it enters what is known as the main sequence phase of its life. This is the longest stage in a star's life cycle, lasting billions of years for stars like our Sun. During this time, the star remains stable, maintaining the balance between the pressure from fusion and the inward pull of gravity. It is during this phase that stars shine their brightest, and their light and heat radiate across space, affecting everything in their vicinity. In the case of our own Sun, it has been a main sequence star for about 4.5 billion years and still has around 5 billion years left in this stage. As the Sun ages, it will eventually run out of hydrogen in its core, and the process of fusion will shift to heavier elements. The core will contract and the outer layers will expand, eventually transforming the Sun into a red giant. This will mark the beginning of the end of its life, as it sheds its outer layers and leaves behind a dense core known as a white dwarf. For more massive stars, the process is much more dramatic. These stars burn through their fuel much more quickly, and as they reach the end of their main sequence phase, they undergo a series of complex nuclear reactions, burning heavier and heavier elements until they can no longer sustain the fusion process. The result is a supernova, a massive explosion that releases an enormous amount of energy. Stellar lifespans, how mass determines fate. The life of a star is a tale shaped primarily by its mass. The size of a star determines not only how long it will live, but also the way it will die. The process of stellar evolution, from birth to death, is intricately tied to the star's mass, specifically how much material it contains. While all stars share certain life stages, their ultimate fates vary dramatically. Mass is the key player in determining the rate at which a star burns its fuel. The more massive a star is, the higher the pressure and temperature in its core, which means the fusion reactions happen at a much faster rate. This increased rate of fusion allows the star to shine brighter, but it also means the star consumes its hydrogen fuel at an accelerated pace. Stars like our Sun, which are considered medium-sized, live for about 10 billion years. They burn their hydrogen more slowly, which means they can maintain a stable state for a longer time. In comparison, a massive star, say one with 10 times the mass of the Sun, might only live for a few million years, just a fraction of the lifespan of a star like our Sun. The intense gravity inside massive stars forces hydrogen atoms to fuse much faster, creating more energy, but it also burns through the star's fuel much quicker. As the star approaches the end of its hydrogen-burning phase, the balance between gravity pulling inward and the outward pressure from fusion begins to shift. This is because the core of the star has consumed much of its hydrogen, and without this fuel, the fusion reactions slow down. In a small star like the Sun, this causes the core to contract and heat up, while the outer layers expand, leading the star to become a red giant. But in larger stars, the process is far more dramatic. As the core contracts, the temperature rises high enough for the star to begin fusing heavier elements, such as helium, carbon, and oxygen. In these massive stars, the fusion process moves rapidly through different elements, creating layers like an onion, where each shell burns a different element at different stages. When a star is large enough, the fusion reactions in its core can reach the point where iron is created. However, this marks the end of the line for the star. Iron cannot be fused into heavier elements to release energy. Unlike hydrogen, helium, and other lighter elements, iron consumes more energy than it produces when fused. This is the crucial moment that determines the death of the star. In a massive star, the core continues to collapse under gravity, and this leads to a catastrophic explosion. The shockwave from this explosion can outshine an entire galaxy for a short period, releasing an enormous amount of energy and scattering heavier elements throughout space. These elements, such as gold, uranium, and platinum, are the building blocks for everything we see on Earth, our planets, oceans, and even ourselves. The explosion of a supernova may leave behind a dense remnant at the core, either a neutron star or, in the most massive cases, a black hole. A neutron star is a stellar corpse so dense that a teaspoon of its material would weigh several billion tons. In the case of the most massive stars, however, the collapse can be so intense that it forms a black hole, a region of space where gravity is so strong that not even light can escape. On the other end of the mass spectrum, smaller stars follow a different path. Stars that are not massive enough to end their lives in supernovae go through a much more gradual, less violent death. A star like the Sun, with a mass of around 1 solar mass, will eventually run out of hydrogen in its core. As the hydrogen fusion slows down, the core contracts and the outer layers of the star expand. These stars become red giants, shedding their outer layers in a gentle wind, forming what is known as a planetary nebula. What remains is the core of the star, which has turned into a white dwarf. A white dwarf is the dense, hot remnant of a star that can no longer sustain fusion. Without the outward pressure from fusion, gravity slowly compresses the white dwarf, but it is supported by a quantum mechanical effect known as electron degeneracy pressure, which prevents it from collapsing further. Over time, the white dwarf will cool and fade away, becoming a cold, dark remnant of its former self. The cooling process takes billions of years, and although a white dwarf no longer shines as brightly as a living star, it carries the memory of the star it once was. A small star undergoes a relatively calm transformation, shedding its layers slowly and leaving behind a peaceful white dwarf. But stars with significantly more mass burn out quickly, leaving behind remnants that can be some of the most extreme and exotic objects in the universe. The remnants of massive stars are some of the densest and most mysterious objects we know of, challenging our understanding of physics. Even though massive stars live short lives compared to their smaller counterparts, they play an essential role in the universe. During their brief existence, they enrich the surrounding space with heavy elements created in their cores. These elements are crucial for the formation of planets, moons, and life. Without the explosive death of massive stars, the chemical building blocks for life would not be as widely distributed across the cosmos. In this sense, the massive stars, despite their short lives, contribute to the ongoing creation and evolution of the universe. The quiet demise and the explosive end. Unlike massive stars, which can continue to fuse heavier elements like carbon and oxygen until they reach the point of iron, low-mass stars do not have enough pressure and temperature in their cores to ignite fusion beyond helium. Without this ability to fuse heavier elements, the star's fusion process comes to an end. The result is the white dwarf, which is composed of material that has already undergone fusion, but cannot undergo further reactions. White dwarfs are incredibly dense objects. Despite their small size, typically only about the size of Earth, they can have a mass comparable to that of the Sun. This means that a white dwarf is incredibly compact, with all of its matter squeezed into a very small space. For instance, a single teaspoon of white dwarf material would weigh about 5 tons on Earth. This extreme density is a result of the collapse of the star's core, which has now condensed into a very small volume. The transition to a white dwarf does not happen immediately after the star becomes a red giant. Instead, this is a process that unfolds over several billion years. As the star loses its outer layers, it gradually exposes its hot, dense core. During this time, the core remains very hot and it continues to radiate energy outward. However, since there is no longer any fusion happening in the core, the white dwarf cannot sustain its brightness for long. Over the course of billions of years, it slowly cools and fades, its once intense light dimming as it radiates its remaining heat into space. Unlike other stellar remnants, such as neutron stars or black holes, which can continue to be active in various ways. White dwarfs are relatively quiet objects. They no longer produce energy through fusion, and they do not exhibit strong magnetic fields or extreme gravity. Instead, they simply cool down over time, gradually losing their heat and becoming more and more difficult to observe. Eventually, after trillions of years, a white dwarf will cool to the point where it no longer emits any detectable light, becoming a cold, dark object known as a black dwarf. However, this process is so slow that no black dwarfs are expected to exist in the current age of the universe, as the universe itself is not old enough for any white dwarf to have cooled completely. The death of a low-mass star is a gradual fading of light, marked by the slow loss of mass and the eventual cooling of the stellar remnant. But this process has a significant impact on the surrounding environment. The planetary nebula from the dying star can enrich the surrounding space with elements like carbon, nitrogen, and oxygen. In this way, the quiet death of a star gives rise to the very building blocks of the universe. Moreover, white dwarfs are not just the end of a star's journey. They also play an important role in the ongoing evolution of the galaxy. As white dwarfs cool and fade, they interact with other stars in their environment. In binary star systems, for example, a white dwarf may interact with a companion star, accreting material from it. If enough material accumulates on the white dwarf's surface, the result can be a nova, an explosion caused by the sudden ignition of the accumulated material. This explosion can briefly reignite the white dwarf, causing it to shine brightly once again before it cools back down. While the process of a star's death and transformation into a white dwarf may seem uneventful compared to the explosive end of massive stars, it plays an essential role in the life cycle of stars and the universe. The material that is ejected into space during the red giant phase becomes part of the interstellar medium, where it can eventually be incorporated into new stars, planets, and life forms. In this way, the quiet demise of low-mass stars is just another chapter in the ongoing story of cosmic evolution. The death of a high-mass star is one of the most dramatic and awe-inspiring events in the universe. Once the core is composed primarily of iron and can no longer generate the outward pressure, the core begins to collapse rapidly, and this process happens extremely quickly, in a matter of seconds. During a supernova, the core's collapse creates a shockwave that sends the outer layers of the star rushing outward at incredible speeds. The explosion releases a staggering amount of energy, equivalent to the energy produced by the star over its entire life, all in a fraction of a second. The outer layers of the star are ejected into space, while the core becomes either a neutron star or a black hole. Neutron stars have a mass typically between 1.4 and 2 times that of the Sun, but which is squeezed into a sphere with a radius of only about 10 kilometers. The collapse of the core is so intense that it forces protons and electrons to combine, forming neutrons. This results in a star composed almost entirely of neutrons, held together by the immense force of gravity. In addition to their incredible density, neutron stars also have strong magnetic fields and can rotate extremely rapidly. When a star collapses into a neutron star, it conserves angular momentum, the same principle that makes a figure skater spin faster as they pull in their arms. As a result, neutron stars can spin at speeds of up to several hundred times per second. This rapid rotation creates strong magnetic fields around the star. The magnetic field is so intense that it can accelerate particles to nearly the speed of light, creating beams of radiation that emit from the star's poles. These beams of radiation are not constant, but sweep across space as the neutron star spins. If the beams are aligned in such a way that they point toward Earth, we can observe regular pulses of radiation. This phenomenon is known as a pulsar. Pulsars emit radiation across a range of wavelengths, including radio waves, X-rays, and gamma rays. The regularity and precision of these pulses make pulsars incredibly valuable for astronomers. The timing of these pulses can be used to study the neutron star's rotation, its magnetic field, and even the material around it. For the most massive stars, however, the collapse of the core is even more dramatic. If the core's mass is large enough, the gravity becomes so intense that it overcomes the pressure from neutrons, leading to a further collapse. This collapse continues until the core becomes a black hole. A black hole is a singularity, a point in space with infinite density, where the laws of physics as we currently understand them break down. The boundary around a black hole is called the event horizon, and once an object crosses this threshold, it can never escape. The size of this horizon depends on the black hole's mass. A black hole with the mass of our Sun would have an event horizon only about 3 kilometers across. But if a star many times more massive collapsed, the black hole could be dozens of kilometers wide, or in the case of the giants that lurk at the centers of galaxies, millions of kilometers. These supermassive black holes anchor galaxies themselves, influencing the orbits of billions of stars. But even the smallest stellar mass black holes are remarkable, because within that small space lies more mass than an entire star, all compressed by gravity's crushing hand. The formation of a black hole is one of the most mysterious and extreme processes in the universe. Once a black hole forms, it continues to pull in any matter that comes too close, growing in size and mass over time. While black holes themselves are invisible, their presence can be inferred by the way they interact with nearby objects. For example, when a black hole pulls matter from a companion star, this material forms a hot, glowing disk around the black hole known as an accretion disk. As the material in the disk spirals inward, it heats up to incredibly high temperatures, emitting radiation that can be detected by telescopes. This process is one of the primary ways that we observe black holes, even though we can never see the black hole itself. The supernova explosion is not only a spectacular end to a high-mass star, but it also has lasting effects on the surrounding universe. The energy released in the explosion is enough to create elements heavier than iron, which are then scattered into space, enriching the interstellar medium. Without supernovae, the universe would be missing many of the elements that make up the planets and life forms we know today. Supernovae act as cosmic forges, creating elements that are essential for the formation of planets and everything else in the universe. Moreover, the shockwaves from a supernova can trigger the formation of new stars. The intense energy and pressure from the explosion can compress nearby gas clouds, causing them to collapse and form new stars. This is how the universe continuously evolves, with the death of one generation of stars paving the way for the birth of the next. Supernovae are therefore not just the end of a star's life, but also a necessary step in the ongoing cycle of star formation and evolution. Galactic evolution: how galaxies live, die, and merge. Galaxies, like stars, are not eternal. They are vast systems of stars, gas, dust, and dark matter, bound together by gravity, and they too go through their own life cycles. When we look at galaxies scattered across the universe, we are not only seeing islands of stars, but also cosmic structures that grow, evolve, collide, and eventually fade. Their story stretches over billions of years, shaping the very framework of the cosmos. The birth of galaxies began not long after the universe itself came into existence. In the aftermath of the Big Bang, matter was spread out in a nearly uniform sea, but tiny ripples and clumps of matter began to pull together under gravity. These small overdensities slowly gathered more material, creating regions where gas could condense and stars could form. Over time, the first galaxies were born. These early galaxies were small, irregular in shape, and full of young stars that burned hot and bright. They were far different from the large, structured galaxies we see today, but they were the seeds of what would come. As galaxies aged, they changed in both form and behavior. Gas clouds inside them collapsed to form new stars, and as stars lived and died, they recycled material back into the galactic environment. The death of massive stars in supernova explosions enriched galaxies with heavy elements, seeding the formation of planets, moons, and so on. The cycle of star birth and death drove the evolution of galaxies for billions of years, shaping their chemistry and appearance. A young galaxy was a place of intense activity, with rapid star formation and chaotic motions. Over time, many galaxies settled into more stable structures, such as the grand spirals we can observe nearby. Not all galaxies took the same path, however. Some grew large and ordered, like the Milky Way, with vast spiral arms sweeping outward from a central bulge. Others became elliptical, massive, but lacking the delicate spiral patterns. Elliptical galaxies are often older, filled with aging stars, and relatively little star-forming gas. Irregular galaxies, by contrast, resisted neat classification, often shaped by collisions and gravitational encounters with their neighbors. The universe is full of these varied forms, each representing a stage in galactic life. Collisions and mergers play a central role in how galaxies evolve. Unlike stars within galaxies, which are so far apart that direct collisions are rare, galaxies themselves can and often do collide. Gravity pulls them together across cosmic distances, and when they meet, the results are spectacular. Their stars, gas, and dark matter swirl and mix, reshaping their structures. In some cases, two spiral galaxies may merge into a single elliptical galaxy, losing their delicate patterns in the process. In others, collisions can trigger bursts of star formation as gas clouds are compressed and collapse into new stars. These cosmic dances are not sudden events, but unfold over hundreds of millions of years, slowly altering the face of the universe. The Milky Way itself is part of this grand process. It has grown through countless mergers with smaller galaxies, swallowing them into its structure. Evidence of these past collisions can still be found in streams of stars stretching across the sky, the remains of galaxies that were torn apart and absorbed. In the future, our galaxy will face an even greater merger. The Andromeda Galaxy, our nearest large neighbor, is on a collision course with the Milky Way. In about 4 billion years, the two galaxies will begin to merge, creating a new, larger galaxy. The stars within will largely avoid direct collisions, but the galaxies themselves will become one, their shapes destroyed and rebuilt in the process. The life of a galaxy is also tied to the fuel it carries. Stars form from cold gas, and without gas, new stars cannot be born. Over time, galaxies use up or lose much of their gas, either by forming stars or by powerful outflows driven by supernova or central black holes. When the supply of star-forming gas runs out, the galaxy grows quieter. It no longer produces many new stars, and its population grows older and redder. These galaxies are sometimes called red and dead, a sign that their days of active growth are behind them. The role of supermassive black holes at the centers of galaxies adds another layer to their story. Nearly every large galaxy appears to have a black hole millions or even billions of times the mass of the Sun at its heart. These black holes can influence their entire galaxies, especially when they actively feed on gas. As matter falls in, it releases tremendous energy, sometimes blasting material back into the galaxy and shutting down star formation. In this way, the central black hole can help determine when a galaxy enters its quieter, aging phase. Galaxies also live within larger structures called galaxy clusters, bound together by gravity on an even grander scale. Within these clusters, galaxies can interact more often, stripping gas from each other or merging into larger systems. In the densest clusters, many galaxies are old and gas-poor, reflecting the harsh environment. Meanwhile, isolated galaxies in the outskirts of space can continue forming stars for longer, fueled by their remaining gas. Even though galaxies seem permanent, they too face an eventual end. As the universe ages, fewer new galaxies form and star formation across the cosmos declines. Galaxies gradually fade as their stars age and die, leaving behind remnants like white dwarfs, neutron stars, and black holes. Trillions of years into the future, galaxies will no longer shine with the bright light of young stars. They will become vast collections of stellar corpses, faintly glowing embers of a once brilliant cosmos. The story of galaxies is one of constant change, spanning from the earliest clumps of matter after the Big Bang to the quiet darkness of the distant future. Their lives mirror the cycles of stars, but on a grander scale, shaping not only themselves, but also the universe as a whole. Each galaxy we see today carries within it the memory of countless births, deaths, and collisions, a record written in the stars that light up the night sky. Dead disk galaxies, the silent remains of once active worlds. When we think of galaxies, it is often the lively, shining spirals that come to mind. We imagine sweeping arms of stars, glowing with young clusters and bright nurseries where new suns are being born. Yet not all galaxies remain this way forever. Some, though shaped like the familiar spirals, fall into silence. These are known as dead disk galaxies, vast systems that have ceased making new stars, their once active lives leaving only a quiet outline of what they used to be. Unlike elliptical galaxies, which often have the appearance of rounded, featureless blobs, dead disks still carry the flat, organized structure of spirals. The difference is that their engines have gone cold. They are like the husks of great machines, impressive in form but stripped of the energy that once kept them alive. At the heart of this transformation lies the raw material of stars, gas and dust. Star formation depends on clouds of cold hydrogen collapsing under their own weight, sparking fusion and giving rise to newborn suns. In a living spiral galaxy, such clouds are scattered throughout the disk, glowing in nebulae and weaving the cycle of stellar birth and death. But in a dead disk galaxy, the supply has been cut off. Whether consumed by earlier generations of stars, blown away by powerful winds, or locked up in regions too hot and stable to collapse, the gas is simply no longer there. The galaxy retains its shape, but its spark is gone. For astronomers, dead disk galaxies challenge long-held assumptions. Spiral structures are typically linked with activity and youth. Elliptical galaxies, by contrast, have long been associated with old stars and quiet times. Yet, here are galaxies that blur the boundary, spirals without life. They show that galactic evolution is not a straight line from active spirals to dormant ellipticals. Instead, it is more complex, with paths that can stall, transform, or freeze in unexpected states. Studying these silent disks has become a window into the processes that govern galactic death. Many appear to have lost their star-forming gas long ago, suggesting that whatever events caused their stillness were dramatic and lasting. Some may have undergone interactions with their surroundings, such as collisions with other galaxies or the draining pull of larger clusters. In dense environments, galaxies can be stripped of gas by a process known as ram pressure stripping. As they move through the hot, thin plasma that fills galaxy clusters, their own reserves are peeled away, leaving behind only stars. In such a case, the galaxy dies not by its own hand, but by the harsh conditions of its cosmic neighborhood. In other cases, dead disk galaxies may owe their silence to internal forces. Central supermassive black holes are known to influence their host galaxies. As matter falls into these dark giants, enormous amounts of energy are released in the form of radiation and jets. This can heat surrounding gas, preventing it from cooling and collapsing into stars. If this process goes on long enough, the galaxy is starved from within. What is left is a fossil of a once lively system, its spiral arms lit only by the fading glow of ancient suns. The appearance of dead disk galaxies is both beautiful and melancholy. Their stars, mostly older and cooler, give them a reddish tint. Without the bright blue light of young stars or the sparkle of stellar nurseries, their arms seem dim, almost ghostly. Observing them is like looking at the bones of a great creature that once roamed but no longer moves. And yet, in their stillness, they tell a powerful story about the universe's constant cycle of energy and change. Dead disk galaxies also provide clues to the fate of systems like our own. The Milky Way is currently active, its spiral arms still cradling the birth of new stars. But this will not last forever. Billions of years from now, after the gas supply has been consumed or ejected, our galaxy too could fade into silence. The brilliant bands of light across our night sky might dim, leaving only the enduring glow of older stars, with no new ones to take their place. In this sense, dead disk galaxies are not only relics, but also warnings of what is to come. Interestingly, Not all of these galaxies are completely uniform in their silence. Some may have small bursts of residual star formation, faint pockets where gas has survived. These are like flickers in an otherwise dark fire, tiny reminders that the processes of life and death in the cosmos are rarely absolute. The balance between activity and dormancy can be delicate, and galaxies may linger in between states for billions of years. In these transitional phases, they reveal how fragile the mechanisms of star-making can be. Modern telescopes have been crucial in uncovering these galactic fossils. The Hubble Space Telescope has captured images of their dim spiral arms, showing shapes that would be mistaken for active galaxies if not for their spectral signatures. More recently, the James Webb Space Telescope, with its ability to peer into the infrared, has begun to reveal details about the populations of stars in these dead systems. By examining their light, astronomers can determine when star formation stopped, piecing together a timeline of their slow demise. These studies suggest that some dead disk galaxies shut down surprisingly early in the history of the universe. This means that galaxies could live full, active lives and then fade long before the cosmos reached its current age. Such findings reshape our understanding of galactic lifespans. They also highlight the role of environment, chance encounters, and cosmic feedback in shaping the fates of entire worlds of stars. Beyond their scientific value, dead disk galaxies capture the imagination. They are reminders that even the grandest structures can fall into silence. They illustrate the fragility of cosmic activity, showing that the engine of creation, once stalled, may not restart. Yet they also point to continuity, as their stars, though no longer replenished, will shine for billions of years more. The galaxies may be dead in terms of creation, but they are not entirely gone. They drift quietly through the universe, carrying with them the memory of brighter times. The story of these galaxies ties into the larger narrative of cosmic aging. Just as stars have lifespans, so too do galaxies. The death of star formation in disks is one step along the path toward a colder, quieter universe. In the far future, if the cosmos continues its expansion and cooling, more galaxies may join the ranks of the silent spirals, until activity itself becomes a rare exception. Looking at dead disk galaxies now is, in a way, a glimpse into that distant future. Each dead disk is a case study, a preserved chapter in the history of galactic evolution. They offer lessons about resilience, about the forces that can sustain or halt creation, and about the balance between light and darkness in the universe. Even in their silence, they speak volumes. Galaxy mergers, the violent rebirth of old worlds. When two galaxies draw near, their mutual gravity pulls them together in a slow but inevitable embrace, one that can last hundreds of millions of years. From a distance, such mergers may appear graceful, as though two vast spirals of stars are weaving around each other in a cosmic dance. But up close, the reality is violent. Stars are ripped from their places, flung into space in great arcs. Gas clouds crash together, collapsing and igniting bursts of new star formation. Entire galaxies are reborn in the chaos. Galaxy mergers are among the most dramatic events in the universe, reshaping old structures into new ones. Unlike the quiet death of an individual star or the silent fading of a galaxy that has run out of gas, mergers represent a form of renewal. A spiral galaxy colliding with another may become an elliptical galaxy, its once orderly disk transformed into a rounder, more chaotic collection of stars. The stars themselves rarely collide, but their orbits are scrambled. What was once a calm and recognizable shape can be torn apart and remade into something entirely different. The most famous example of a future merger is happening in our own cosmic neighborhood. For billions of years, the Milky Way and Andromeda will twist and pull at each other, eventually combining into a single, much larger galaxy, often referred to as Milkomeda or Milkdromeda. For any civilizations that may exist within those galaxies at that time, the night sky will be filled with breathtaking arcs of stars and glowing clouds of gas. These encounters are not rare. When we look at giant elliptical galaxies, we are often looking at the results of ancient collisions, their stars stirred together into a more uniform shape. Even our Milky Way carries scars of past mergers. Each one added to the mass of the Milky Way, contributing its stars and dark matter to the growing system. The violence of a merger is not just about motion and shape, it is also about energy. When gas clouds from two galaxies crash into one another, they compress, heating up and collapsing under gravity. This sparks rapid star formation, which can light up a galaxy, creating bright regions filled with young, hot blue stars. Some of these stars live short lives and explode. Out of the chaos, new generations of stars and planets are born. But these same events can also feed the dark hearts of galaxies. During a merger, gas and dust are driven toward the center, falling into the waiting black hole. As the material spirals inward, it releases enormous amounts of energy, sometimes igniting a quasar, a blazing beacon that can outshine the rest of the galaxy combined. These brilliant objects can be seen across billions of light years, reminders of the violent mergers that power them. Even small galaxies are not spared. Dwarf galaxies often fall into the grip of larger ones, their stars and gas stripped away in tidal streams. Some are absorbed entirely, leaving behind only faint traces of their former existence. This process continues endlessly as small galaxies feed larger ones and larger ones combine into giants. The universe is, in a sense, built on mergers, with each new collision adding to the structures we see today. The scale of these events is difficult to comprehend. A single merger can take billions of years from beginning to end. The first encounter may pull the galaxies into elongated shapes, sending great arcs of stars into space. Then, after looping around one another, the galaxies may pass apart, only to be drawn back together again. With each pass, they lose energy until they finally combine into one. For the stars inside, this process means a complete rewriting of their orbits. A star that once circled calmly around the center of a spiral disk may find itself flung into the outer halo of the new galaxy, or sent on a chaotic orbit through a dense, crowded core. The very structure of the cosmic web, with its clusters and superclusters of galaxies, is shaped by these interactions. Without mergers, galaxies might remain smaller and less diverse. The richness of forms we see in the universe, the spirals, the ellipticals, the irregulars, all owe something to the constant pull of gravity drawing galaxies together. Astronomers study mergers not only to understand the past, but also to predict the future. Computer simulations allow us to watch, in accelerated form, the slow process of two galaxies combining. These simulations reveal the fine details of how stars and gas are redistributed, how tidal tails form, and how central black holes grow. Observations with telescopes like Hubble and the James Webb Space Telescope give us snapshots of mergers at different stages, from the first contact to the final coalescence. By piecing these together, we can reconstruct the long story of galactic evolution. In the grand timeline of the universe, mergers are milestones. They mark moments of transformation when old galaxies give way to new ones. Even on scales so vast they seem eternal, nothing is static. Everything changes, and in that process, the seeds of new stars and worlds are sown, ensuring that even in violence, creation continues. The Fermi paradox, searching for life in a graveyard of stars. The silence of the universe is one of its greatest mysteries. When people look up at the night sky, they imagine that somewhere, among the countless stars, there must be other beings staring back at their own skies, wondering the same thing. The sheer numbers almost demand it. The Milky Way alone holds hundreds of billions of stars, many with their own planets. Beyond that, there are trillions of other galaxies. Even if only a tiny fraction of these worlds were capable of supporting life, the odds seem overwhelming that intelligent life must exist somewhere else. Yet, when we listen, when we search, we hear nothing. This is the essence of what is called the Fermi paradox. It is not simply the question of whether life exists, but why the universe seems so empty, when, by all reason, it should be alive with voices. The paradox is named after physicist Enrico Fermi, who, during a casual conversation in the 1950s, is said to have asked a simple but haunting question. Where is everybody? His point was that if the universe is so vast, and if civilizations have had billions of years to rise and expand, then it should only take a small portion of that time for one of them to spread across the galaxy. Even moving slowly, across millions of years, a civilization could travel from star to star, building colonies and leaving behind evidence of their presence. The fact that we see none of this suggests that something is missing from our understanding. Either intelligent life is far rarer than we think, or it does not last very long once it appears. The more astronomers learn about planets, the more pressing this question becomes. When telescopes first began to detect exoplanets in the 1990s, no one knew how common they would be. Now, we know that planets are everywhere. Many stars have entire systems, some of them with rocky, Earth-like worlds in the right zone for liquid water. If Earth is not unique, and if nature repeats itself often, then the ingredients for life should be scattered throughout the galaxy. Life on Earth appeared quickly, almost as soon as conditions allowed it. That suggests it may not be difficult for life to begin. And yet, when it comes to advanced civilizations, the silence remains absolute. Some scientists think the problem lies with the way we are looking. Our search for alien life often focuses on radio signals, because radio waves can travel vast distances across space and still be detected. For decades, projects like SETI, the search for extraterrestrial intelligence, have scanned the skies, listening for any sign of a signal that could only come from a technological source. A deliberate broadcast, or even a faint leak of transmissions from another world, would reveal that we are not alone. But so far, the radio sky has remained quiet. There have been occasional blips and strange signals, but none that stand up to repeated study. The silence may not mean that nobody is out there, but that they are not using the kind of technology we expect, or that they are not trying to reach out. Another possibility is distance. The galaxy is so large that even if a civilization were broadcasting signals, they might not have reached us yet, or they may be too faint for our instruments to detect. Light takes time to travel, and so does any form of communication. If another world is 1,000 light years away, then even a powerful broadcast would take 1,000 years to arrive, and our reply would take another 1,000 years to go back. In that sense, conversations across the stars may be happening, but on timescales that are far beyond our ability to notice in a single human lifetime. Humanity has been using radio for just over a century, a blink of an eye compared to the age of the universe. It may be that civilizations exist, but their windows of communication are brief. A species might develop technology, broadcast signals for a short time, and then disappear due to war, environmental collapse, or other disasters. If this pattern is common, then the galaxy could be filled with the ruins of civilizations that no longer exist. We might simply be unlucky, living in an era when no one else is speaking. Stars live and die over billions of years, creating the heavy elements that make life possible, but their deaths also sweep clean the regions around them. Planets can be scorched, atmospheres stripped away, and any life that existed may be erased. Civilizations too may face their own versions of this cycle, with progress followed by decline. It is possible that the silence of the universe is not because life never existed, but because life has always been fragile, rising only to fall again before it could spread far enough to be noticed. Perhaps advanced civilizations do not reveal themselves because they choose not to. This is sometimes called the zoo hypothesis. The idea is that older, more advanced beings might watch us without making contact, allowing us to develop without interference, much as humans observe animals in the wild. If this is true, then the silence is not an absence, but a choice. Another suggestion is that civilizations may stay quiet because they fear attracting attention. In a universe where resources are limited, it could be dangerous to broadcast your location. Silence, in this view, may be a form of survival. On the other hand, there is the chance that intelligence itself is exceedingly rare. While simple life may be common, the leap to complex thinking beings might be so unlikely that Earth is one of the only places it has happened. We know that for most of Earth's history, life remained simple. Multicellular organisms appeared only after billions of years. Intelligence, tool use, and technology came even later, and in the vast sweep of evolutionary time, they may be a brief and unusual phenomenon. If this is the case, then we may be the exception rather than the rule. The Fermi paradox does not offer easy answers, and that is what makes it so powerful. It forces us to confront not only the question of whether we are alone, but what it means if we are. A universe filled with silence could mean that we are the first, stepping into a vast cosmic arena with no one else yet present. Or it could mean that others came before us and are now gone, their traces erased by time and distance. In both cases, the emptiness of the skies becomes a reminder of our own fragility. New telescopes, capable of scanning exoplanet atmospheres for signs of life, may soon give us clues. Astronomers are beginning to look not only for radio signals, but for what are called technosignatures, any evidence of technology such as unusual energy use, strange patterns of light, or even massive structures that might surround stars. Each new method adds to our ability to test the paradox. If we find even the faintest hint of another civilization, it would change everything. If we find nothing, the silence itself will grow louder, pressing us to wonder why the universe, so vast and ancient, seems to be ours alone. The great filter, why civilizations might always expire. By the laws of probability alone, there should be countless societies spread across the galaxy. Yet when we look into the night sky, we see only silence. The great filter is one possible answer. It suggests that at some point, life hits a barrier that it almost never crosses. Civilizations may rise, but something prevents them from lasting long enough to spread to the stars. To understand this idea, imagine the history of life as a series of hurdles. The first hurdle is the origin of life itself. On Earth, it happened quickly, perhaps within a few 100 million years after the planet cooled. But we don't know how easy that step really was. It could be common everywhere, or it might have been an incredible stroke of luck. After life begins, the next hurdle is complexity. For billions of years, Earth was covered only in simple, single-celled organisms. Multicellular life, the kind that can build bodies and brains, took an extraordinarily long time to appear. Then comes intelligence. Dinosaurs ruled the Earth for over 150 million years without ever building tools or language. Intelligence may be far from inevitable. And even if intelligence evolves, the leap to technology and civilization is another hurdle. Many species are smart, but only humans built cities and spacecraft. The great filter could exist at any one of these stages. If it lies in the past, it means we are among the rarest of the rare. Life may be common, but intelligent, technological beings might be almost non-existent. In that case, our existence would be a miracle of cosmic luck. But if the great filter lies ahead, the picture changes. That would mean civilizations like ours often reach a certain level of development, only to destroy themselves or collapse before becoming interstellar. If that is true, then our future may be far shorter than we hope. The idea becomes even more unsettling when we think about the kinds of filters that might exist in the future. One obvious possibility is self-destruction. Advanced societies eventually create technologies powerful enough to end them. On Earth, nuclear weapons are a clear example. For the first time in history, humanity has the ability to destroy itself in a single day. Other dangers lurk as well. Artificial intelligence, if not controlled, could outgrow us. Bioweapons could spread uncontrollably. Climate change could destabilize entire ecosystems and societies. The Great Filter may not be a single event, but a web of risks that multiply as civilizations advance. Another possible filter is resource collapse. Civilizations might depend on limited supplies of energy or raw materials. As they grow, they could strip their planets bare, unable to sustain themselves. Our own world offers hints of this. Forests vanish, oceans heat, and minerals are dug from the earth faster than they can be replaced. A society that cannot balance growth with sustainability might burn out quickly, leaving little trace behind. From the viewpoint of the universe, entire civilizations might rise and fall in the blink of an eye. Cosmic dangers could also play a role. Supernovae, gamma-ray bursts, or asteroid impacts can erase worlds in an instant. On Earth, life has survived many mass extinctions, but intelligence and civilization are fragile. A single catastrophic event might be enough to reset a planet's progress back to zero. If such disasters strike often, few civilizations would ever have time to grow beyond their home planet. The Great Filter could even be a matter of distance and time. Civilizations might survive, but space is vast. The stars are spread so far apart that contact becomes almost impossible. Radio signals fade and spacecraft crawl across the void at speeds far too slow to bridge galaxies. Perhaps many civilizations exist, but none ever meet. Each one is like a flickering candle in the dark, bright for a while, then gone, with no chance to find its neighbors. If civilizations were common and long-lasting, we should see evidence. Massive engineering projects, colonized planets, or signals stretching across the stars. The fact that we do not suggests that something cuts them short. Either they rarely get started, or they do not survive long after they begin. For us, the Great Filter is not only a scientific puzzle, but also a mirror. If it lies ahead, then we are racing toward it even now. Every new technology we create could be a doorway to our survival or our destruction. The filter could take the form of choices we make, whether we learn to live wisely with our power or fall victim to it. There is another way to see the Great Filter, not as a sentence, but as a challenge. If most civilizations do not survive, then perhaps survival requires extraordinary effort. It may demand cooperation on a scale rarely achieved, or innovations that allow a species to step off its fragile home planet and spread into space. In this view, the filter is not impossible to pass, but very, very hard. Most societies fail, but a few succeed and endure. If we want to be one of those few, we will need to recognize the risks and act with care. The thought is sobering, but also motivating. The Great Filter reminds us that civilizations are not guaranteed to last forever. They are fragile, temporary things in a dangerous universe. But it also suggests that the future is not fixed. The filter might still be ahead, but it does not have to claim us. Our survival may depend on how we use the knowledge we have and whether we can learn to balance growth, technology, and the limits of our world. And so, the Great Filter hangs over our story like a shadow. It might be a relic of the past, already behind us. It might lie in the future, waiting to test us. Or it might take many forms, spread across the path of any civilization that dares to grow. In all cases, it speaks to the mystery of why the universe seems so quiet, and whether we will find a way to keep our own light burning in the dark. Life's existence in the galactic graveyard. Is the universe too harsh for complex life? Planets and galaxies like ours seem like the natural nurseries of life, full of energy and material for growth. But when we turn our eyes to the older, quieter regions of the cosmos, the galactic graveyards, the picture changes. Here, the universe reveals a much harsher face. Galaxies that once blazed with bright stars now fade into dim, silent collections of ancient suns. Gas and dust, the fuel needed to make new stars and planets, have thinned out or disappeared. Instead of a landscape of birth and growth, we find a realm of endings and survival under extreme conditions. Can life, especially complex life, truly exist in such an environment? Galaxies in their younger days are rich in gas and dust, the raw material for stars, planets, and the heavy elements that living systems require. These elements, carbon, oxygen, nitrogen, phosphorus, and others, are forged in the hearts of stars and spread through space when those stars die. In a young galaxy, the cycle of starbirth and death creates an ever-renewing supply of the chemistry that life needs. But in a galactic graveyard, this process slows and eventually stops. With fewer new stars forming, there are fewer supernova enriching the galaxy with heavy elements. Over time, the supply of fresh material dwindles, and what remains is locked inside ancient stars, or scattered too thinly to form new worlds. For life, especially life that needs planets with stable conditions, this lack of resources poses a serious barrier. Even if planets formed earlier in the galaxy's history, they face another problem: the aging of their parent stars. In old galaxies, the stars that remain are often smaller, dimmer red dwarfs, or swollen, unstable giants nearing the end of their lives. Red dwarfs burn for trillions of years, but they are far from hospitable. Many of them flare violently, releasing radiation that could strip the atmospheres of nearby planets or sterilize their surfaces. Giant stars, on the other hand, may offer warmth for a short while, but are doomed to unstable endings, blowing off their outer layers and leaving only dense white dwarfs behind. A planet orbiting such a star might survive physically, but its environment would change so drastically that maintaining life would be almost impossible. The calm, steady sunlight that complex life seems to need is rare in these stellar graveyards. Radiation adds yet another layer of danger. In the active parts of the universe, galaxies are bustling with energy, but much of it is balanced by fresh star formation and protective magnetic fields. In dead or dying galaxies, conditions can be very different. Supermassive black holes often linger in the centers of these galaxies, and while the galaxy itself may be quiet, the black hole can erupt from time to time. Streams of high-energy particles and radiation can flood the surrounding regions, sterilizing entire zones where planets might exist. Without the constant churning of young stars and gas clouds to absorb and scatter this energy, the galaxy becomes a harsher environment for any fragile biospheres. Complex life, which depends on stability, would find survival in such an environment nearly impossible. The chemical balance of the universe also shifts with age. Early galaxies often had stars poor in metals. Astronomers use this term to describe elements heavier than hydrogen and helium. As time passed, star formation enriched galaxies with metals, creating the conditions for rocky planets like Earth. But in dead galaxies, without ongoing star formation, this enrichment comes to an end. Over trillions of years, stars burn through what remains, and the galactic chemistry grows stagnant. Planets that might have been rich in the elements needed for life are fewer and fewer. If life ever began in such a galaxy, it would face the challenge of sustaining itself in an environment where new sources of the building blocks are not replenished. Some might argue that microbial life, simple and hardy, could endure in such places. This is possible. Microbes on Earth have shown remarkable resilience, surviving in boiling vents at the bottom of the ocean, in frozen Antarctic deserts, and even in radioactive waste. Perhaps similar life forms could persist on the hidden subsurface oceans of planets or moons orbiting aging stars. But when we ask about complex life, life capable of building ecosystems, evolving intelligence and forming civilizations, the odds shrink dramatically. Complex life needs not just survival, but stability over long timescales, a stable climate, steady sources of energy and protection from catastrophic radiation. These are exactly the qualities missing in the graveyards of galaxies. Perhaps the universe itself has set natural limits on how far life can go. It could be that the very conditions that allow galaxies to form and evolve also guarantee that they will eventually turn hostile. A galaxy may offer a golden age where life can rise and flourish, but this age is temporary. As the galaxy burns through its fuel, the window for complex life narrows and eventually closes. If this is true, it may help explain why we have not yet detected alien civilizations. Perhaps they are as short-lived as the active phases of their galaxies, and by the time we look for them, the stars that once supported them are already fading. On Earth, it took billions of years for complex organisms to appear, and even longer for intelligence to rise. If we had been placed in a galaxy already far along its path to death, there might not have been enough time for us to emerge before the stars dimmed and resources ran out. This suggests that the existence of complex life may depend not only on the right kind of planet and star, but also on the right moment in cosmic history. Too early, and the galaxy lacks the heavy elements to form Earth-like worlds. Too late, and the galaxy has already burned through its fuel, leaving little room for growth. This paints a sobering picture. The universe may be filled with countless planets, but many of them may orbit stars in regions that have already gone quiet. To us, they would appear as ancient, silent worlds, unlikely to host anything more than microbes clinging to survival. The grand story of life may not be written evenly across the cosmos, but may be tied to certain epochs, certain phases in the life of galaxies, where the conditions align for complexity to arise. Outside of those windows, the universe may simply be too harsh, too unstable, and too empty of the resources needed for life to thrive. We live in a galaxy still alive with star formation, with a star stable enough to support life for billions of years on a planet with just the right chemistry and balance. We may be the fortunate few living in one of the rare gardens where complexity can bloom. The silence of the galaxy may not mean life is impossible. It may only mean that life has a narrow window to emerge and that most of the cosmos has already passed beyond it. Stellar remnants and the fate of habitable planets. When a star like our Sun reaches the end of its fuel supply, it swells into a red giant. During this stage, the inner planets are roasted and in some cases swallowed entirely. Earth itself will not survive this transformation. Its surface will be scorched beyond recognition. Eventually, the outer layers of the dying star drift away into space, forming a glowing planetary nebula, while the dense core shrinks into a white dwarf. It no longer shines through fusion, but instead glows faintly as it cools over billions of years. For any planets that manage to avoid being destroyed during the red giant phase, the change in environment is dramatic. Instead of basking in a stable, life-sustaining warmth, they orbit a fading ember. If life ever existed there, it would have to adapt to extreme cold and darkness, a task that may prove impossible for complex organisms. For more massive stars, the story is even harsher. Their cataclysmic end can rip apart entire planetary systems. The shockwaves and intense radiation obliterate any nearby planets, stripping atmospheres, boiling oceans, and sterilizing surfaces in an instant. What remains at the heart of the explosion is not a gentle neighbor. The intense radiation fields around neutron stars and the violent gravitational pull of black holes make them hostile environments for any surviving planets. Yet planets do sometimes survive. Astronomers have detected planets orbiting pulsars. These so-called pulsar planets are some of the strangest worlds we know of. They exist in environments filled with deadly radiation, bombarded by high-energy particles. The fact that they are there at all is remarkable, but few believe such places could support life. If anything, they stand as grim reminders that planets can endure even when conditions make them utterly uninhabitable. White dwarfs, on the other hand, may provide a glimmer of hope for habitability, at least in theory. Because they cool slowly, they can provide a faint but steady source of energy for billions of years. If a planet is the right distance away, it could potentially sustain liquid water on its surface. In fact, some astronomers have suggested that life might eventually emerge around white dwarfs, long after most stars like our Sun have burned out. The catch is that planets would need to migrate into this narrow habitable zone after the star's transformation, since anything close to the star during its red giant phase would have been destroyed. Even then, the window of habitability may be limited as the white dwarf continues to cool. It is a fragile balance, one that may rarely, if ever, produce stable conditions for complex life. When galaxies run out of the gas needed to form new stars, they become cosmic graveyards filled with stellar remnants. Their skies would be dotted not with the brilliance of new stars, but with fading white dwarfs, neutron stars, and black holes. The planets that remain in such places would orbit dead or dying suns, bathed in cold and silence. Even if some of these worlds once had oceans, atmospheres, and perhaps even life, those days would be over. Without new stars to form and new energy to feed ecosystems, the galactic environment becomes hostile to growth. In such graveyards, the chances for life to persist, let alone thrive, grow vanishingly small. The fate of habitable planets, then, seems tied to the inevitability of cosmic decay. Every world that forms is given only a temporary lease on habitability, dictated by the lifespan of its star and the changing conditions of its galaxy. For Earth, that lease is about 5 billion years more, until the Sun becomes a red giant. For planets orbiting massive stars, the window may last only a few million years, a blink in cosmic time. Even planets around long-lived stars eventually face decline, as those stars grow old, expand, and leave only remnants behind. And yet, there is a strange persistence in the universe. While stars die and planets freeze, the materials that once supported life do not vanish. The carbon, oxygen, and nitrogen that once formed the building blocks of biology remain scattered across the galaxy. They may end up locked inside cold white dwarfs, trapped in the crusts of rocky planets, or drifting as dust between the stars. These elements can still play a role in future cosmic cycles, even if those cycles take trillions of years to unfold. The graveyards of planets and stars are not entirely empty. They are filled with the raw ingredients of new worlds, and perhaps, in some distant future, new forms of life. The fate of black holes: will they evaporate or consume the universe? Black holes feel like eternal traps, devouring everything that comes too close and holding onto it forever. For much of modern astronomy, they were thought of as the ultimate full stops of the universe, objects that consume but never give back. But in the 1970s, a surprising idea shook that view. Stephen Hawking suggested that black holes are not completely black. Instead, they should give off a faint glow, a slow leakage of energy that means even these monsters of gravity may one day vanish. This idea, called Hawking radiation, forever changed how we think about the fate of black holes, and with it, the long-term future of the cosmos. To understand why, we need to picture the strange way the universe works at its smallest scales. In the world of quantum physics, empty space is not truly empty. It bubbles with what are called virtual particles, pairs of matter and antimatter that constantly appear and disappear. Normally, these pairs cancel each other out almost instantly, leaving no trace. But near the edge of a black hole, the event horizon, something different can happen. One particle of the pair may fall into the black hole while the other escapes. To an outside observer, it looks as though the black hole has emitted radiation. And because energy must come from somewhere, the black hole loses a tiny bit of its mass. This process is unbelievably slow. For a black hole the size of our Sun, the time it would take to completely evaporate is about 10 to the power of 67 years, a number so vast it is hard to imagine. For the supermassive black holes at the centers of galaxies, the timeline grows to 10 to the power of 100 years or more. That is 100 billion trillion times longer than the current age of the universe. For now, black holes look eternal. But on the grandest timeline imaginable, they too may fade. The evaporation begins gently, almost imperceptibly. For billions of years, the black hole would remain stable, its pull unchanged. But as it grows smaller over unimaginable spans of time, the radiation it gives off intensifies. The black hole slowly warms, glowing more and more until, in its final moments, it releases an enormous burst of energy. A black hole that once consumed stars would end its life in a brief but brilliant flash, evaporating completely in a final burst of light and heat. If this picture is correct, then the universe's most powerful engines are not eternal prisons, but temporary features. Eventually, in the farthest future we can imagine, there will be no black holes left at all. Instead, the universe will be filled with only faint radiation, cooling and spreading endlessly. This paints a picture of a cosmos that not only grows quiet, but also loses its darkest shadows. Yet not everyone is certain this will happen. Hawking radiation has never been directly observed. The effect is far too faint for us to detect with current technology. Our best evidence for it comes from the mathematics of quantum theory and general relativity, two frameworks that are powerful but not yet fully reconciled with one another. Some physicists suspect that our picture of black holes may still be missing a piece. Perhaps black holes do not evaporate completely. Perhaps they leave behind tiny, stable remnants, objects that carry the last trace of their existence. Or perhaps our understanding of gravity itself will need to change in ways that could alter this story. Another possibility is that black holes could play an even more active role in the universe's future. Instead of slowly vanishing, they may continue to dominate the cosmos long after stars have burned out. As galaxies fade and stellar remnants drift apart, black holes will remain as the last powerful anchors of matter. They could pull in stray stars, planets, or even other black holes, merging into larger and larger structures. In this view, black holes may not fade away quietly, but continue to reshape the universe deep into its dark future. Imagine a time trillions upon trillions of years from now, when stars have all gone dark and galaxies have dissolved into scattered matter. Black holes would still lurk, swallowing anything that comes too close. Whole solar systems could disappear into their depths. Even if evaporation does eventually win, for a staggeringly long stretch of cosmic history, the universe could belong to them. Which picture is more likely? Will black holes eventually evaporate into nothing, leaving the cosmos empty? Or will they remain, consuming stray matter and dominating the universe until the very end? The truth may depend on aspects of physics we do not yet understand. Hawking radiation is a bridge between two great theories that do not always agree. To fully answer the fate of black holes, we may need a deeper theory of everything, one that unites the small and the large. If black holes do evaporate, then the universe seems destined for a slow and total fading, with no structure left anywhere. If they remain, the cosmos may stay shaped by their presence far longer, with giant black holes standing as the last monuments of creation. Either way, the timeline is so immense that our own age of stars and galaxies will look like a brief spark compared to what lies ahead. Cosmic zombies, the potential for resurrecting dead stars. A star burns through its fuel, transforms into a red giant, collapses, explodes, or settles into a faint ember of its former self. The story seems complete, a line drawn under a chapter that can never be reopened. Yet there are always exceptions and strange phenomena. The idea of stars that are revived or reanimated under certain circumstances may sound strange, but the universe has shown hints that such things may not be entirely impossible. A dead star, in most cases, is a white dwarf, neutron star, or black hole. For a long time, these endpoints were seen as permanent. Nothing could bring a star back from such a fate. But over time, observations revealed that sometimes these corpses do not rest quietly. They can interact with their surroundings in violent, unpredictable ways, making them look like they've come alive again. One of the most well-known examples of a dead star's resurrection comes from white dwarfs in binary systems. A white dwarf may sit next to a still-living companion star, quietly orbiting, invisible against the glare of its partner. But as the companion evolves and expands, gas from its outer layers can spill over onto the white dwarf. This flow of fresh hydrogen piles up on the white dwarf's surface, eventually igniting in a sudden nuclear burst. The white dwarf flares into brilliance, creating what astronomers call a nova. To an observer, the dead star appears to wake from slumber, shining with newfound energy. In truth, it has not been reborn in the same sense as a young star, but the outburst is dramatic enough to make it appear resurrected. These nova events can repeat many times, as long as the white dwarf keeps stealing fuel from its companion. Even more dramatic are the cases where a white dwarf gathers too much material. If it crosses a critical mass limit, the star can no longer support its own weight. At that point, it collapses and explodes in a supernova, leaving nothing but scattered ashes behind. This is not so much a resurrection, as it is a final, catastrophic blaze of glory. Still, it shows that even a star thought to be dead can find a way to burn again, if only briefly, and in spectacular fashion. Neutron stars, too, sometimes behave like cosmic zombies. A neutron star may spend millions of years quietly spinning, its magnetic fields fading, its energy slowly leaking into space. Then, through some unknown trigger, it can suddenly flare to life. Magnetars, which are a special kind of neutron star, are famous for this. These objects unleash powerful bursts of radiation that can outshine entire galaxies for a few moments. It is as if the star, long thought to be fading, suddenly shakes itself awake. The cause of these flares is still debated, but many scientists believe they are the result of magnetic fields twisting and snapping, releasing enormous amounts of stored energy. Sometimes, neutron stars can also switch on as pulsars. Some pulsars are known to stop emitting and then, after years or even decades, start again. It is almost as if the star fell into a deep sleep and then reawakened. Why this happens is still a mystery. But such behavior reinforces the idea that death in the cosmos is not always absolute. Sometimes there are second acts. Perhaps the most eerie resurrection happens when a neutron star merges with another neutron star or a black hole. In these collisions, titanic forces rip apart matter and release bursts of energy so intense they can be seen across billions of light years. The gravitational waves from such events ripple through space-time itself. These explosions create heavy elements. In a sense, the neutron stars are destroyed, but what follows can be seen as a new creation, the birth of elements, the stirring of matter into new forms. What died has given rise to something new. Some astronomers wonder whether black holes themselves could one day spit out energy, or particles, in ways that might resemble a star's rebirth. Hawking radiation suggests that black holes can evaporate over unimaginable timescales, but in their final moments, as they shrink to nothing, they may release intense bursts of energy. To distant observers in that far future, it might look like the last flare of a star that has long since been gone. It would not be a true resurrection, but the echo of one, the last heartbeat of something that defied death for eons. There are also stranger ideas, not yet proven, that keep the discussion alive. Some physicists have proposed that under certain exotic conditions, dead stars could capture enough gas or dark matter from their environment to reignite nuclear fusion in their cores. If this were possible, it would mean a star could, in effect, start shining again after billions of years of silence. Such events, if they ever occur, would be unimaginably rare, and we may never witness one. But in a universe as vast as ours, even rare things can sometimes find a stage. The line between life and death in the cosmos is not always sharp. Stars do not simply vanish into nothingness when their fuel runs out. They leave behind remnants that can still interact, flare, or even explode under the right circumstances. A white dwarf stealing gas, a neutron star pulsing again, a black hole releasing its final breath. Each of these is a kind of resurrection, even if only partial or temporary. The universe is full of objects that should be dead, but somehow still find ways to stir, shine, and even terrify. Death in the cosmos, as in life, is often more complicated than it first appears. In the cold graveyards of galaxies, where stars should lie in silence, there may still be echoes of light, flickers of energy, and whispers of resurrection. The role of rogue planets in a dying universe. When stars die, their planets often face destruction. Some are swallowed as their suns expand. Others are frozen in the darkness once the light of their star goes out. But not all planets are tied forever to their parent systems. Some are cast loose, ejected from orbit by the chaotic dance of gravity, or flung into the void when stars collide, die, or are torn apart. These lonely wanderers are called rogue planets, worlds without a sun. They drift through space with no steady source of light or warmth. Rogue planets have been seen as curiosities, hidden and faint, almost impossible to detect against the black background of space. Yet when we imagine the distant future of the universe, a time when stars are long gone, rogue planets take on a new role. They may become the last survivors of the cosmos, still carrying with them a shadow of complexity in a universe that is otherwise heading towards silence. In the youth of galaxies, when stars and planets are forming, gravity can be as much a destroyer as a builder. Young stars often form in clusters, tugging at each other and disturbing the orbits of newborn planets. A close encounter with another star can sling a planet out of its system entirely, freeing it from its sun. The planet does not disintegrate, it simply carries on, traveling through space forever. Later in cosmic history, when stars grow old and unstable, they can also eject their planets. A red giant star swelling outward can destabilize orbits, while a supernova explosion can rip entire systems apart, sending planets flying into the dark. By these and other means, countless planets are set free, becoming wanderers in the cosmic wilderness. Some estimates suggest that in our own galaxy there may be more rogue planets than stars, billions upon billions of them, adrift in silence. For most of their existence, rogue planets are dark, cold, and nearly invisible. Without a star to heat them, their surfaces plunge into deep freeze. To us, they may seem like lifeless rocks or frozen gas giants, wandering aimlessly, but under their icy shells, there may be secrets. A planet with a thick atmosphere could trap some heat. A large planet with internal radioactive decay might sustain warmth deep inside. Most intriguingly, a rogue planet with a subsurface ocean protected under kilometers of ice could harbor liquid water, shielded from the void outside. On Earth, we know that life can exist without sunlight, thriving instead around deep-sea vents powered by the heat of the planet itself. If something similar could exist on a rogue planet, then these dark worlds might not be entirely barren. They could be the hidden sanctuaries of life in a universe where stars eventually burn out. Imagine a universe tens of trillions of years from now, when galaxies have spread apart so much that light from one can no longer reach another. By then, most stars will be gone. The small, dim stars that live the longest will have exhausted their fuel. White dwarfs, neutron stars, and black holes will be all that remain of stellar systems. Yet rogue planets, once cast loose, will still exist. Unlike stars, they do not rely on fusion or radiation to survive. They are inert, long-lived, and resilient. They are fragments of the old universe, drifting endlessly while the cosmic stage around them grows colder and darker. Where once galaxies blazed with trillions of suns, the distant future may hold only scattered embers and wandering planets. In this way, rogue planets are not just survivors of stellar death, they are survivors of cosmic death. Their significance lies not only in their endurance but also in what they might carry with them. A rogue planet could serve as a vessel, preserving chemical complexity or even life long after stars are gone. Civilizations, if they still existed, might cling to such worlds as refuges. Advanced beings could hollow out the crust of a rogue planet, tapping into geothermal energy to create artificial warmth. They could shield themselves beneath thick ice, protected from cosmic rays and the vacuum outside. Such an existence would be far removed from the bright, open worlds we imagine today. But in a dying universe, survival might mean adapting to the cold and the dark. Rogue planets would be among the last possible homes. There is another role rogue planets may play. As galaxies age and stars fade, the gravitational interactions between remnants may still continue. A rogue planet could be captured again, pulled into orbit around a stellar remnant, or even a black hole. In that case, it might briefly become part of a new kind of system, orbiting in eternal night around a collapsed star. Such captures would be rare in the vast emptiness of space, but rogue planets could still participate in the last dance of matter in the cosmos. Even in decline, gravity does not stop weaving new patterns. In the deep future, as black holes evaporate and even the last traces of starlight vanish, rogue planets would continue their journey. They are not indestructible, of course. Given enough time, their atoms themselves may decay, depending on the laws of physics. But on timescales beyond comprehension, trillions upon trillions of years, they will persist longer than the stars that once gave them birth. In the silence of the far future, a rogue planet could drift alone through the void, carrying within it the memory of a once bright universe. If life ever found a way to cling to such a place, then rogue planets could represent not just the last physical survivors, but the last living survivors too. They would be both tombstones and arcs, showing that the cosmos, no matter how bleak, never loses all of its complexity in one final instant. Instead, it fades slowly, piece by piece, leaving scattered worlds to drift in the dark. The story of rogue planets is the story of resilience, of fragments of creation that outlast their creators. and in the endless night of a universe approaching heat death, they may be the last sparks of a forgotten age. Dark matter and the invisible graveyard. Dark matter has always been a silent player in the story of the universe. Unlike stars, which shine and die in dramatic explosions, or galaxies, which sweep across the heavens with billions of suns, dark matter does not call attention to itself. It does not glow, it does not radiate heat, and it does not interact with light. Yet it holds the cosmos together. It acts as the scaffolding on which galaxies form and live out their lives. Without dark matter, the familiar structures of the universe would never have taken shape, and long after the last stars have faded, dark matter will still be there, an invisible skeleton of reality stretching across the cosmic graveyard. In the early universe, dark matter shaped the first galaxies. It clumped together under gravity, forming invisible wells that pulled ordinary matter in. Over time, stars lit up inside these wells and galaxies were born. But when those galaxies eventually run out of fuel and their stars burn out, dark matter remains. It does not die or decay in the same way as ordinary matter. Its presence continues, vast and hidden, silently guiding the motion of whatever is left. If the universe becomes a place of cold, faint remnants, black dwarfs, neutron stars, black holes, dark matter will still surround them, stretching across empty distances and tying them together into unseen webs. Scientists still do not know what dark matter really is. It could be a particle unlike anything we have detected. It could be something stranger, a field or effect we barely understand. But what makes it important for the story of the far future is its sheer persistence. Stars can burn out, galaxies can drift apart, even black holes can evaporate over unimaginable timescales. Dark matter, however, may endure without limit. If it does, then it will be the last great structure of the cosmos, forming the framework of a universe otherwise emptied of energy and light. Imagine looking out into darkness and seeing nothing, but knowing that beneath that black canvas, vast halos of unseen material are still there. They no longer hold glowing stars, but they continue to curve space, to bend paths of objects, and to define the architecture of emptiness. The great cosmic web, once so beautifully lit by galaxies along its threads, will still exist, though it will be a ghostly web, made only of what cannot be seen. The role of dark matter in such a time becomes even more fascinating. In an expanding universe driven apart by dark energy, dark matter is the counterweight, the part that resists dispersal and clings to itself through gravity. Even as galaxies fly farther apart, each one remains wrapped in its invisible cocoon of dark matter. This means that while the grand structures of the cosmos will vanish from view, smaller systems may remain bound together for much longer. A cluster of collapsed stars, black holes, and perhaps even wandering planets could continue to orbit within a dark matter halo, holding onto each other for countless eons. These could be the last islands of structure surrounded by oceans of nothing. But what happens to dark matter itself? Does it last forever? Some scientists wonder whether dark matter could decay over very long timescales. If so, then even the invisible skeleton of the universe might crumble away one day. But no evidence yet suggests that this is happening. The best we know, dark matter has remained stable since the beginning of time, and there is little reason to think it will vanish anytime soon. If it truly endures without limit, then the final universe will not be entirely empty. It will still have this strange, invisible substance stretched across its depths, a faint shadow of the universe's younger self. There would be no light, no heat, and no stars to see, yet gravity would still move things. Invisible halos would continue to guide the paths of the last remnants, black holes gliding slowly through space, rogue planets wandering endlessly, dust clouds adrift in nothingness. Without dark matter, even these leftovers might drift apart more quickly. But because of it, there could still be some structure, even in the deepest silence of time. The cosmic graveyard would not be completely flat. It would still have a faint outline of its old skeleton. One way to imagine this is to think of a great cathedral that has lost its roof, its stained glass, and its candles. The stone arches remain, but they are empty and silent. Dark matter is like those arches. It is the shape that remains after the light is gone, the unseen structure that gives form to the void. To walk among it would be to wander in a world where everything is hidden, where the skeleton of creation is all that is left. There is also a strange possibility that dark matter could be the final foundation for whatever forms of life or intelligence might arise in the deep future. If energy is scarce, could some unimaginable life form learn to use the invisible substance itself? This is far beyond our understanding, but it is a thought that lingers when we consider how often life has surprised us. Just as the first microbes once fed on chemical energy in rocks long before plants and animals existed, perhaps the distant future could hold beings that live in ways we cannot yet imagine, drawing sustenance from what looks to us like nothing at all. If that ever happens, dark matter would not just be a skeleton of the universe, it would be its last hidden well of possibility. For now, all we can do is wonder. Dark matter is invisible to our eyes and instruments except through its gravity. Yet its importance cannot be overstated. It is the silent architect of galaxies, the hidden thread of the cosmic web, and possibly the last survivor of all when the rest of the universe has faded away. The universe's future seems silent and cold, but perhaps it is more accurate to say that it will become invisible. Dark matter will still be there, a cosmic graveyard beneath the surface, holding up a universe that to us would look like nothing at all. Beyond the observable universe, the cosmic graveyards we'll never see. Our observable universe is a bubble with a finite radius. Beyond it lies a vast expanse we will never be able to witness. Even with the most powerful telescopes, even with billions of years of patient observation, the edge of the observable universe is a horizon we cannot cross. And yet, beyond this horizon, the universe continues. Entire galaxies, clusters, and cosmic structures live, age, and die in silence, hidden forever from human eyes. We know that the universe extends farther, but its contents are inaccessible. Over time, as cosmic expansion continues to accelerate under the push of dark energy, more and more galaxies slip past this horizon. Once gone, their light can never catch up, and they vanish from our sight forever. From our point of view, it is as though the universe is slowly erasing itself. They may be some of the richest parts of the universe, filled with galactic giants, star-forming nurseries, and massive black holes. Yet, they will all eventually undergo the same fate as the regions we can see. Stars will burn through their fuel. Supernovas will scatter elements into space. Black holes will consume matter before evaporating over unimaginable timescales. Without new energy to replenish them, these faraway galaxies will fade into silence. What makes this tragedy greater is that we will never witness their final acts. They are lost to us, separated not by distance alone, but by the very laws of physics. Our universe may be far older and stranger than what we can observe. If there are regions beyond our horizon that evolved differently, they could be home to cosmic events we cannot even imagine. Entire epochs of star formation, galactic collisions, and stellar deaths could be playing out endlessly, with no record that will ever reach us. There could be entire clusters where stars burned faster and died earlier, leaving nothing but cold remnants. To us, they are beyond existence. The accelerating expansion of the universe makes this separation worse with time. In the far future, even the galaxies we see today will slip into invisibility. Eventually, only our local group of galaxies will remain in sight. All else will vanish beyond the horizon, leaving us stranded in a dark, lonely pocket of space. This means that future observers, billions or trillions of years from now, will live in a universe that looks drastically smaller than ours. For them, the cosmic graveyards will not only be unseen, but also unknown. But what if we think of it differently? Beyond the horizon, galaxies are not only fading, but also being born. We cannot see them, but they must exist. New stars ignite, new planets form, new possibilities emerge. If life exists in those unreachable realms, it will evolve under skies we will never know. Entire civilizations may rise and fall in isolation, never aware of us, just as we cannot be aware of them. Each is trapped in its own cosmic bubble, separated forever by the expansion of space. This gives the universe a strange dual character. It is both vast beyond comprehension and limited by the boundaries of observation. No matter how advanced a civilization becomes, no telescope and no technology can pierce the veil beyond the observable universe. The speed of light is not just a challenge, it is a fundamental barrier. This means that some mysteries are permanent. The unseen graveyards of distant galaxies will remain invisible not because we lack tools, but because the universe itself forbids us from ever reaching them. Even so, the mind reaches outward. Scientists speculate about what lies beyond based on what we see inside our observable bubble. Patterns of structure, the distribution of galaxies, and the laws of physics suggest that the universe beyond our view must look much the same. But this is still an assumption. There may be surprises, vast regions where matter is arranged differently, where expansion has unfolded in unique ways, or where unknown forces have left their marks. The graveyards of those galaxies may not follow the same timeline as ours. Perhaps the true death of the universe is already unfolding beyond our reach. Maybe entire regions have already grown cold and lifeless, with stars gone and black holes evaporated. If so, then the end of everything is not a distant possibility, but a present reality, creeping inward from unseen corners of the cosmos. In that case, the observable universe is like a shrinking island of light surrounded by an ocean of darkened ruins. Graveyards remind us of the passage of time, of stories completed, of endings that shape meaning. The cosmic graveyards beyond our sight are no different. They remind us that the universe is not eternal in the way we might wish. They reveal that even in infinity, loss exists. Each unseen galaxy is a reminder that all things end, even if those endings are hidden. The heat death of the universe, a cosmic funeral. In the farthest stretches of time imaginable, beyond the lifespan of stars, beyond the collapse of galaxies, beyond the last black holes evaporating into nothingness, there waits a final chapter. It is the idea of the heat death of the universe, the ultimate cosmic funeral. Unlike the violent explosions of supernovas or the sudden collapse of a dying star, this ending comes quietly, gradually, and inescapably. It is not one event, but the sum of countless processes slowly winding down over unimaginable spans of time, until the universe no longer has the ability to change. To picture this end, we must imagine time stretched out to lengths so vast that even trillions of years become insignificant stepping stones on the way to still greater emptiness. The concept begins with the second law of thermodynamics. At its core, this law tells us that energy naturally spreads out, moving from concentrated useful forms into more disordered, unusable ones. In the universe today, stars shine because they are hot, compact furnaces of energy, surrounded by the cold vacuum of space. That difference between hot and cold makes energy flow possible. It lets stars burn, planets orbit, and life exist. But over time, as stars die and energy is used up, the differences grow smaller. Energy spreads more evenly across space. Slowly, the contrast that drives activity fades away. Without contrast, nothing moves, nothing shines, nothing lives. To see how this unfolds, we can walk forward through the deep future of the cosmos. First, stars like our Sun exhaust their fuel and fade. For a time, galaxies continue to sparkle with the light of younger stars. But over billions of years, these too reach their ends. Star formation slows, then stops. The great spiral arms of galaxies, once bright and full of energy, dim into shadows. What remains are the remnants, faint embers of white dwarfs, cold cinders of neutron stars, and the invisible mouths of black holes. Even in this stage, the universe is not yet dead, only aging. Energy still exists in concentrated forms, locked inside matter, swirling within black holes, or lingering as radiation in space. But as time marches forward, even these reservoirs begin to drain away. White dwarfs, once glowing faintly, cool over trillions of years until they vanish into invisible black dwarfs. Neutron stars may persist as silent spheres of dense matter, but with no heat or light to give, they become little more than frozen monuments to what once was. Black holes, though seemingly eternal, are not immune either. Through the slow process of Hawking radiation, they evaporate, shrinking into nothing over timescales that dwarf the lifespan of any star. As these structures fade, the universe begins to smooth out. Energy, once clumped into stars and galaxies, spreads more evenly. With no new sources of concentrated power, there is nothing left to restart the process of creation. Galaxies empty, space grows darker, and the silence deepens. The universe enters what is sometimes called the dark era, when all that remains are thin traces of radiation, scattered particles, and expanding space. The expansion of the universe only adds to this decline. With every passing epoch, galaxies drift farther apart, stretching the space between them. Today, we can see billions of galaxies across the cosmos. But in the distant future, most of them will slip beyond the cosmic horizon, pulled away faster than light by the expansion of space itself. For observers living trillions or quadrillions of years from now, their universe will look far smaller, limited only to the remains of their local galaxy, if even that survives as a coherent structure. The grand view of the cosmos, filled with billions of lights, will vanish. As the universe ages into this distant future, the temperature of space itself continues to drop. The cosmic microwave background, the faint afterglow of the Big Bang, already chilled to just a few degrees above absolute zero, will cool even further. Over time, it will thin until it is indistinguishable from darkness. The very fabric of the universe will approach absolute zero, the lowest temperature possible, where particles barely move and no energy can be extracted. The most haunting aspect of the heat death is not that energy disappears, it never truly vanishes, but that it becomes useless. Energy evenly spread across space cannot do work. It cannot flow from one place to another, cannot be harnessed to power stars or life. In this sense, the universe dies not in a violent end, but in a quiet exhaustion. All the drama of creation, the fiery birth of stars, the collisions of galaxies, the explosions of supernovas, was only a brief spark compared to the endless calm that follows. If the universe inevitably drifts toward this final frozen state, then all the structures we see today, from galaxies to living beings, are temporary patterns in an ocean that will one day be flat and still. Some thinkers find this vision bleak, a story where even the greatest achievements fade into silence. Others see beauty in the idea that we live during the universe's brief period of brilliance, a time when stars still shine and life can still exist. The heat death becomes not just an ending, but a reminder of how precious the present truly is. Even so, some scientists wonder whether the heat death is truly inevitable. Could unknown physics alter this picture? Might the universe cycle back into a new beginning? Or could dark energy itself change over time, shifting the fate of everything? These questions remain open. For now, the heat death stands as the most widely accepted view of the far future, a story rooted in the laws of thermodynamics and the slow unfolding of entropy across the cosmos. To imagine the heat, death is to imagine silence stretched across infinity. It is the ultimate graveyard, not of a single star or galaxy, but of everything that ever was. Yet in contemplating it, we also glimpse the remarkable truth of the present, that we are here, in a cosmos still full of light, still alive with energy, still capable of wonder. The funeral may come, but for now, the universe still sings. The end of information. Will the universe forget its own past? In the beginning, the universe was a place overflowing with information. Every particle, every photon, every interaction carried a record of what came before. The afterglow of the Big Bang, still visible as the cosmic microwave background, is an imprint of the infant universe. The patterns of galaxies, the motions of stars, even the isotopes inside planets, all tell a story of processes that took place long ago. In many ways, The universe is a library written in matter and energy, with each structure containing a page of its history. But like any library, pages can be damaged, ink can fade, and over great enough stretches of time, even the strongest records can be lost. Information in physics is not just knowledge, it is tied to the very arrangement of matter and energy. When a star forms, its light is a kind of signal carrying information about its temperature, its mass, and its age. When it explodes as a supernova, it sends out a final message in the form of radiation and heavy elements. These are pieces of data the universe distributes freely. The same is true for black holes, galaxies, and even the faint whisper of radiation drifting through the cosmic void. Each moment is a record, but as the universe ages, these records begin to disappear. In every direction, the clarity of the cosmic story begins to blur. The expansion of the universe is the first great eraser. As galaxies move farther apart, their light stretches into longer wavelengths. Eventually, the glow of galaxies beyond a certain distance will redshift into invisibility. To an observer far in the future, it will appear as if those galaxies never existed at all. Their information is not destroyed immediately, but it becomes unreachable. From a local point of view, the universe looks emptier, stripped of the pages that once told of its vastness. Black holes complicate the picture further. According to classical physics, anything falling into a black hole disappears forever, its information sealed away. This created a deep paradox. Does the universe lose data whenever a black hole swallows it? Quantum physics suggests otherwise. Hawking radiation proposes that black holes slowly release radiation that encodes, in some scrambled form, the information they once trapped. If true, then information is not destroyed, but transformed, scattered back into the universe in the faintest whispers of heat. Yet this process is unimaginably slow, and even if information eventually leaks back, it is so scrambled that it may never be reconstructed. The story it once told would be effectively erased, replaced with noise too faint to interpret. Entropy is the ultimate archivist in this story. As time marches forward, the universe tends toward equilibrium, where differences in temperature, pressure, and energy even out. Entropy does not destroy information outright, but it makes it harder to access. Imagine a book shredded into pieces and scattered in the wind. In theory, the information is still present in the fragments, but the effort required to piece it back together grows impossible. The same is true for the cosmos. Over trillions upon trillions of years, particles will drift farther apart, energy will spread more evenly, and the records of past events will dissolve into patterns that no longer reveal their origins. Information becomes unrecoverable, not because it vanished, but because it is lost in the noise. One of the strangest possibilities is that even the laws of physics themselves may not be eternal. If constants change, if space-time itself decays, then the framework that defines what information means could crumble. What would it mean for the universe to forget not just the arrangement of particles, but the rules that gave those arrangements order? The cosmic library is not written in stone. It is written in patterns that depend on the fabric of reality itself. If the fabric frays, the writing disappears. Some thinkers wonder whether the universe itself is a kind of computer, processing information at every moment. If so, then the end of information would be like shutting down the last machine. When energy differences vanish, when particles no longer interact in meaningful ways, there is nothing left to compute. The memory of the universe becomes frozen, unchanging, without even the faint activity of new events to add to its record. In this view, the universe does not just forget its past, it stops thinking altogether. For billions of years, existence has been a conversation between matter, energy, and time. Stars burned their messages across the sky. Galaxies formed grand patterns, and life itself arose as a complex reader of the cosmic text. But all stories move toward their end. In the distant future, when the last black holes have evaporated and the last particles drift silently in the void, the record will be gone. The universe will hold no memory of the Big Bang, no trace of the galaxies, no echo of life. The library will be empty, the pages blank. The night sky is a museum of information, offering glimpses into billions of years of history. Every photon is a message from the past, still legible, still carrying meaning. Perhaps this is the gift of our time, that we exist in an age when the library is still open and the stories are still there to be told. Dimensional decay. Could the fabric of reality unravel? Space feels like a container, and time feels like a flow. But what if these are not permanent fixtures? What if the very framework that makes motion, distance, and existence possible is itself subject to decay? In the far reaches of time, long after galaxies have dimmed and stars have turned to ash, the universe may face a stranger kind of end, the fading of dimensions themselves. This is the idea of dimensional decay, where the fabric of reality does not just stretch or cool, but begins to unravel. The thought seems almost impossible at first. Space has always been three-dimensional, at least as far as our experience goes. One can move left and right, forward and backward, up and down, and all of physics is built upon this foundation. Add in time as a fourth dimension, and you have the stage on which every star has burned, and every atom has collided. But theories in physics suggest that dimensions may not be fixed in number or stability. In fact, some models of the early universe suggest that extra dimensions might have existed, only to collapse or curl up into tiny hidden forms, too small for us to see. If dimensions can appear or shrink away, perhaps they can also decay, collapsing again in the deep future. This raises the strange possibility that the universe may not simply run out of energy or collapse into a singular point, but instead lose the very scaffolding that makes matter and energy possible. Imagine a sheet of cloth stretched across a frame. At first, it holds its shape, smooth and firm. Over time, though, the threads begin to loosen. The weave unravels. Eventually, the fabric ceases to exist as a surface at all. It is only scattered threads with no pattern. In the same way, reality might lose its dimensional weave. Space itself could become undefined, with no direction in which matter could move. This kind of decay would be a quiet dismantling. Galaxies, if any remained, would find that the distances between their stars were no longer meaningful. Atoms might no longer be able to hold together, because the space in which their particles interact would collapse into something else, or perhaps into nothing. Even time might lose coherence, no longer flowing as a steady sequence of moments but breaking down into fragments that have no order. This is not entirely detached from science. String theory, for example, imagines that the universe may have more dimensions than the ones we observe, dimensions that are hidden away at tiny scales. If these dimensions can be unstable, they could also change or disappear. In another idea, known as quantum gravity, space-time itself is not continuous, but made up of tiny, discrete pieces, like pixels on a screen. If those fundamental units of space-time break down or reorganize, the larger fabric they create could also unravel. It is also possible that the laws we take as permanent are only temporary. They may be emergent, arising out of deeper conditions, and if those conditions change, the laws could vanish. This means that dimensional decay would not just be the loss of space, it would be the loss of law, the collapse of the rules that allow the universe to be coherent. If such a decay occurred, there is little that any kind of life or intelligence could do to resist it. In a heat death scenario, one might imagine life adapting to colder and rarer environments, finding new ways to use the last traces of energy. But in dimensional decay, adaptation would have no meaning, because adaptation assumes a framework of time and space in which actions can be taken. If space is gone, there is nowhere to go. If time is gone, there is no sequence in which choices can exist. This end would not be survivable, because it would erase the very idea of survival. Still, one could wonder whether something might remain after such a decay. When a structure breaks down, sometimes its parts create something new. A collapsed star becomes a neutron star. Could the collapse of space and time give rise to another kind of framework, perhaps with different dimensions or rules. In that case, dimensional decay would be a transformation, as if the threads of the universe's fabric were rewoven into a new pattern. But whether that would allow life, or anything resembling matter, is uncertain. It could be a cosmos so alien that our words for distance, time, or being would not apply. We might be unable to detect such decay, even if it were beginning. Our measurements of cosmic expansion and energy rely on the assumption that space and time are stable. If those dimensions were slowly shifting in ways too subtle to notice, we might interpret the signs as something else, like unexplained noise or anomalies in physics. Dimensional decay could be happening beneath our feet, beneath the atoms in our bodies, and we would not know until it reached a tipping point. For now, no experiment has confirmed that dimensions can unravel, though some physicists continue to explore whether the universe might face such an end. It stands as a reminder that reality itself may be less solid than we believe. We take for granted features that may not be permanent fixtures of existence. They may be temporary conveniences, granted by a universe that one day could take them away. Dark energy and the accelerating universe, stretching time and space. When astronomers first began to measure the expansion of the universe, they expected to find that gravity was slowing everything down. Galaxies were moving apart, yes, but the pull of their combined mass should have been working against that outward push. Over time, the universe should have been expanding more slowly, with the possibility of one day halting and reversing. But when careful observations of distant supernovae were made in the 1990s, the data revealed that the expansion was not slowing, it was speeding up. This discovery shook the foundations of cosmology. It suggested that some mysterious force was driving galaxies apart faster and faster, stretching the very fabric of space itself. That mysterious force was given the name dark energy. Unlike ordinary matter or even dark matter, dark energy is not something that clumps together or gathers into galaxies. Instead, it seems to be spread evenly throughout the cosmos, woven into space itself. Its presence acts like a kind of pressure, but instead of pulling things together, it pushes them apart. This push is incredibly weak on small scales, which is why it doesn't affect the planets in our solar system or the stars in our galaxy. But across billions of light years, its influence becomes overwhelming. The more space there is, the more dark energy there is pushing, and the faster the universe stretches. The idea of space itself stretching can be hard to imagine. A common way to picture it is to think of dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they are traveling across the surface, but because the surface itself is expanding. The same is happening to galaxies in our universe. They are not flying through space like bullets, they are being carried apart as the fabric of space expands. What dark energy does is accelerate that inflation, as though someone keeps blowing harder and harder into the balloon. This acceleration has dramatic consequences for the long-term fate of the cosmos. In a universe without dark energy, gravity might eventually slow expansion enough for galaxies to remain in closer reach of one another. Instead, dark energy ensures that the gaps will only grow. Galaxies that are far away today will eventually move so quickly from our point of view that their light will never reach us. They will fade beyond a cosmic horizon, leaving only the galaxies that are gravitationally bound to us. This means that billions of years from now, future observers may only see the faint glow of their own galaxy, with no sign of the wider universe. For them, the evidence of expansion, and even the very existence of a cosmos beyond their galactic home, could be erased. Dark energy makes time itself feel stretched in a strange way. As the universe grows, the rate of its expansion grows too, which changes how we think about the flow of cosmic history. The further into the future we look, the more empty and lonely the universe appears. Regions that were once accessible to telescopes or signals will slip forever out of reach. Space is not only expanding, but accelerating toward a future where communication and travel across galaxies will become impossible. Light from a distant galaxy takes billions of years to reach us. But as dark energy stretches space, It also stretches that light, shifting it toward longer wavelengths. This redshift makes distant galaxies appear dimmer and redder the further away they are. Eventually, galaxies become so redshifted that their light thins into invisibility, leaving the night sky darker and emptier with each passing eon. The stars themselves will still shine for a while, but the grand view of a vibrant, expanding cosmos will disappear. What makes dark energy even more puzzling is that its strength does not diminish as the universe expands. Ordinary matter becomes less dense as space grows, because the same number of particles are spread over a larger volume. Radiation thins out even faster as its energy gets stretched by expansion, but dark energy stays the same. No matter how large the universe becomes, it continues to exert the same effect per unit of space. This property suggests it is not a substance in the usual sense, but something tied to the nature of space itself. Some scientists propose that dark energy could be the energy of the vacuum, a kind of baseline energy that exists even in empty space. Others imagine it as a new type of field that permeates the cosmos, changing how gravity behaves on vast scales. But so far, no experiment on Earth has been able to directly measure it. We only see its fingerprints in the way galaxies move, and in the patterns of light left over from the Big Bang. If dark energy continues to act the way it does now, the universe will keep accelerating forever. But there are more extreme possibilities. If the force of dark energy grows stronger with time, it could eventually tear apart galaxies, solar systems, and even atoms in a scenario sometimes called the Big Rip. In this vision of the future, everything would be pulled apart as space itself stretched infinitely fast. On the other hand, if dark energy weakens or changes its nature, the universe might settle into a slower pace or even reverse, collapsing back into a final crunch. For now, the best evidence points to a future of endless acceleration. Galaxies will drift apart until each one becomes an island of stars surrounded by darkness. Beyond their edges, the universe will be unreachable, locked away by the relentless expansion of space. In this way, dark energy not only shapes the present, but dictates the distant destiny of all that exists. It stretches not only space, but also the meaning of time, creating a cosmos that is both vast and fleeting, filled with countless galaxies but destined to hide them from view. The cold, empty universe, life beyond the heat death. Could anything in any form still exist in a cold, empty universe? If life is known for its persistence, perhaps even the quietest and most fragile form of it could stretch on beyond what we think of as an ending. To imagine such a future, it is helpful to think of what life requires. Every living thing that we know depends on a flow of energy. On Earth, plants capture energy from the sun, animals feed on that energy indirectly, and even bacteria in deep oceans find chemical energy to sustain themselves. Energy is the spark that allows order to resist the natural pull of disorder. But in the far future, when the universe reaches its heat death, that spark will be almost impossible to find. Energy will be spread out so evenly that there will be no natural flow from one place to another. Without gradients, without differences in temperature, there is no way to draw power. And yet, some have wondered whether the last flickers of energy could be stretched, drawn out in ways that allow some form of activity to continue. Physicists sometimes speculate about extremely slow processes, civilizations or beings that operate on timescales so long that what seems like nothing to us could be meaningful to them. Imagine a mind that only thinks once every trillion years, waiting patiently for tiny shifts in the background radiation, or the rare collision of decayed particles. To us, such a life would appear frozen, like stone. But from its perspective, there might still be thought, memory, and even awareness. Others have suggested that perhaps structures could form not from energy as we know it, but from the very fabric of space-time. Quantum mechanics hints that empty space is not truly empty. Tiny fluctuations occur constantly, giving rise to virtual particles that flicker in and out of existence. In today's universe, these fluctuations are so small that they barely matter. But in the deep future, when all other sources of energy are gone, they may be the only things left to work with. Could advanced forms of life, if they somehow survive to that time, learn to draw on these fluctuations? Could they find a way to spark activity in a sea of stillness? Some scientists have considered the possibility that information itself could serve as a kind of life in the far future. If matter is gone and energy is useless, perhaps the patterns of information stored in quantum fields could be preserved in some form. Life, after all, can be described as information organized in a way that resists decay. The cells in your body are patterns of molecules, carrying the code of DNA. Could there be a way for patterns of information to continue even when the physical carriers of life are no longer available? This idea moves into very speculative territory, but it reflects the drive to imagine survival in the face of absolute stillness. The heat death of the universe is not expected for at least 10 to the power of 100 years, a number so large it defies true comprehension. By then, not only will stars and galaxies be gone, but even protons may have decayed, leaving nothing but radiation and the occasional particle drifting in endless darkness. If life, or something like it, were to exist in such a time, it would be unrecognizable to us. It might exist as rare, scattered pulses of activity in an otherwise silent ocean. Philosophers sometimes describe this imagined existence as a ghost life, one that clings on, not in the way we understand, but in ways that stretch the very definition of what life means. Would such beings, if they could think, even consider themselves alive? Or would they simply be the last echoes of a universe that once held stars, galaxies, and worlds filled with wonder? Perhaps the laws of physics as we know them do not allow for persistence once energy has reached complete equilibrium. In that case, the story of life would be a brief chapter in the larger history of the cosmos, a flame that flared brightly for a time and then went out, leaving only darkness. To some, this idea is troubling. To others, it is poetic, a reminder of the preciousness of the moments we have now. Still, the imagination does not stop there. Some theorists wonder whether new universes could be born even out of the ashes of heat death. If quantum fluctuations are real, perhaps one of them could grow into something larger, a bubble of energy that expands, igniting a new Big Bang. In that sense, the universe may never truly die. Instead, it may give birth to countless new universes, each with its own story. If that is true, then perhaps life, or something resembling it, will always find new ground to take root in. Our science gives us outlines, probabilities, and mathematical models, but it cannot yet tell us exactly what will happen. What is clear is that life as we know it cannot continue in such a universe. But whether some new, almost unrecognizable form of existence might arise is a question that lingers. It is a question that reflects not only the limits of physics, but also the endless reach of human imagination. Perhaps in the shadows of nothingness, something unexpected waits, something that could turn the end into another kind of beginning. The decay of space. Will the fabric of the universe fade away? Space is seen as the quiet backdrop against which everything else unfolds. Stars burn, galaxies drift, black holes swallow, and planets circle, all within the invisible fabric we call space-time. It feels permanent, like a canvas that cannot tear, bend, or fade away. Yet some physicists have asked the question, what if this very canvas is not eternal? What if the fabric of space itself can decay, slowly eroding until nothing remains, not even emptiness? This idea sounds strange, almost unsettling, because space already seems like nothing. But nothing in physics is not the absence of existence. It has rules, structure, and energy built into it. Space expands. It bends under the pull of matter, and it allows time to tick forward. It may seem passive, but it is deeply active in shaping everything we know. If space-time itself has a kind of built-in fragility, then the long future of the cosmos may not just be cold or dark. It may be unstable at its very foundation. One way scientists explore this possibility is through the idea of vacuum decay. In physics, the word vacuum means the lowest possible energy state of space. But what if the vacuum we live in is not truly the lowest state, but only a temporary one? Imagine a ball resting in a shallow valley. It looks stable, it doesn't roll away, and it could stay there for ages. But beyond the hills there might be a deeper valley, a more stable resting point. If the ball were to roll over into that deeper valley, the state of the whole system would change. In the same way, our universe could be resting in what is called a false vacuum, not the deepest possible version of reality. If this is true, then space as we know it could one day decay into a new form. A bubble of true vacuum might suddenly appear in some distant region, perhaps triggered by quantum fluctuations. This bubble would expand at nearly the speed of light, rewriting the very rules of physics inside it. The forces that hold atoms together, the structure of time, even the existence of matter as we know it, could vanish or transform beyond recognition. For anything caught in its path, there would be no warning and no escape. To outside observers, this would be the ultimate erasure, as if the universe itself had rewritten its code. This is a deeply speculative idea, but it flows naturally from the equations of quantum field theory, the same mathematics that describes particles, energy, and the early universe. Some researchers point to the properties of the Higgs boson, the particle discovered in 2012, as a possible clue. The measured mass of the Higgs seems to suggest our vacuum might be metastable, balanced precariously between stability and collapse. If so, then space-time itself carries within it the possibility of eventual decay. Other scenarios consider whether the expansion of the universe itself weakens space-time. As dark energy drives galaxies apart, space stretches faster and faster. Could this stretching tear the very fabric, leaving behind nothingness in a Big Rip scenario? In this picture, the acceleration does not stop. It grows so extreme that it eventually overwhelms all forces. Galaxies are torn away from each other, stars ripped apart, planets shredded, and finally atoms themselves pulled into nothing. What remains would not be a new structure of space, but the collapse of structure itself. In the Big Rip, space-time does not just fade, it unravels. Even if no dramatic ripping or bubble decay occurs, there is still the quieter but equally haunting prospect of the gradual thinning of space-time. Just as heat spreads evenly in the vision of heat death, one could imagine the fabric of space becoming less dynamic, less structured, more ghost-like as time rolls on. The stretching could dilute not only matter and energy, but also the capacity of space-time to hold anything at all. In the far future, beyond trillions upon trillions of years, we may face a cosmos where space exists only in name, with no properties left to sustain the flow of events. The most extreme versions of this ask whether time itself would come to an end. If space-time is not permanent, then the ticking of moments may not be either. Our universe could reach a final pause, where time no longer advances because the medium that carries it, the fabric of space, has ceased to exist. To us, locked inside the current form of reality, this is almost impossible to picture. What does it mean for time not to pass? How can anything end if there is no future? It is like asking what lies beyond the edge of existence itself. And yet, even if these scenarios are terrifying, they may also be natural. After all, nothing in the cosmos seems eternal. Stars burn out, galaxies fade, black holes evaporate. Why should space itself be exempt from change? We are used to thinking of it as eternal and invincible, but perhaps it is just another actor in the cosmic drama, destined to have an ending. If that is true, then the universe is not a stage that holds the play. It is part of the play itself, rising and falling with everything else. Could life ever survive such a change? Could intelligence somehow anticipate and adapt to a rewritten universe? Or would all memory of our existence be wiped clean? Is the decay sudden, like the burst of a bubble, or slow, like the fading of an echo? Each version paints a different picture of the far future, but all share one thing in common: the recognition that the universe is not guaranteed to last in the form we know it. If vacuum decay is real, it could begin anywhere, at any time, without warning. It could be happening right now, billions of light years away, a bubble expanding invisibly through the cosmos. Or it may never happen, and our vacuum could endure forever, We simply do not know. The fate of space itself may rest on properties we have barely begun to measure. For now, all we can do is imagine. We gaze at the stars and wonder about galaxies, about black holes, about heat, death, and expansion. But behind all of these lies the deeper question: is the very fabric holding it all together stable? If it is not, then the ultimate ending of the universe is not just cold emptiness. It is transformation into something unprecedented, or perhaps the end of reality itself. The decay of space is not simply another step in cosmic evolution. It is the possibility that there may come a time when even the idea of a universe no longer makes sense. Time's end, the final moments of the universe's clock. What happens to time when everything else has ended? Time is usually thought of as the stage on which all events play out, but if the stage itself collapses, what does that mean for the story of the cosmos? To imagine the final moments of the universe is not only to think about the death of matter and energy, but also about whether time can come to a halt. In our everyday lives, time is so constant and reliable that it feels separate from the things inside it. We wake up, the clock ticks forward, and we assume that no matter what happens, time will always be there, keeping count. Yet in physics, time is not independent. It is bound up with space, woven into the very geometry of the universe. Together, they form space-time. And space-time is not unchanging. It bends, stretches, and evolves. That means time itself is part of the story of the universe. It has a beginning, tied to the Big Bang, and possibly an end, tied to the ultimate fate of everything. As the universe expands, time stretches along with space. The ticking of the cosmic clock is not the same everywhere, nor has it been the same throughout history. In the very early universe, time advanced through a storm of energy, particles, and rapid inflation. Later, it slowed down into the calmer rhythm of galaxies and stars. Today, it ticks in a way shaped by dark energy as expansion accelerates. Looking into the far future, when galaxies are pushed further and further apart, one wonders, does time simply continue, endlessly marking moments in an empty void? Or does it too run out? One way to think about this is through the heat-death scenario. In this vision of the far future, energy becomes evenly spread out, and no more useful work can be done. If nothing ever changes, if no new events occur, then what meaning does time have? Time is, at its heart, a measure of change. Without change, does time still exist, or is it indistinguishable from non-existence? Some scientists argue that in this state, time would lose its practical meaning, even if mathematically it continues. The universe would not end with a bang, but with a silent fading into timelessness. But there are deeper possibilities. In physics, time is not only a concept of change, but also a dimension tied to the structure of space-time. If space itself stretches without limit, driven by dark energy, then time must also stretch. In this case, the clock would keep ticking forever, but at a pace so stretched that in the farthest future, the difference between one moment and the next could grow beyond comprehension. In an empty and accelerating universe, time could dilute in the same way matter and energy do, still present, but stretched so thin that its reality becomes ghostly. On the other hand, if the universe does not expand forever, but instead meets some catastrophic end, time might not stretch endlessly. If a big rip tears apart galaxies, stars, atoms, and even space-time, then the fabric of time would shred. The clock of the universe would not only stop, but be destroyed, leaving no framework in which before or after could exist. In such a case, the final moment of time would arrive as an absolute boundary. Beyond it, there would be nothing, not even the absence we usually imagine when thinking of void. Another possibility lies in the decay of the vacuum. If this field is not perfectly stable, it could one day collapse, creating a bubble of new physics within which the rules of reality might be rewritten, including the structure of time. If such an event occurs, it would erase the timeline of our universe, cutting it short abruptly. The last tick of the clock would be swallowed, and time as we know it would be no more. Even more speculative is the idea that time is not fundamental at all. Some physicists suggest that time might emerge from deeper physical laws. In this view, time is not a basic ingredient of the universe, but something that arises from the way matter and energy interact. If so, when those interactions fade, when the universe drifts into a state of maximum entropy, time might dissolve. The universe would not only be empty of stars and galaxies, but also empty of the very flow that carried them through existence. Our sense of time is built from memory and expectation. We remember what has happened, and we imagine what will happen. If the universe reaches a point where no events occur, where no new moments can be distinguished, then the difference between now and then disappears. For a conscious observer, this would mean slipping into an eternal present, with no change to mark the passing of moments. It is not so much the end of time as the loss of its meaning. Some thinkers speculate about what could lie beyond time's end. This is difficult to imagine because every thought we have is tied to the notion of time moving forward. To picture existence without time is like trying to see without space. It feels impossible. Yet if time is part of the universe's structure, then if that structure dissolves, so too might time. In that case, there is no beyond. The story simply ends, not because something new follows, but because there is no framework left for anything to happen. And yet, there remains the possibility of cycles. Some cosmological theories suggest that time might not end permanently, but instead reset. In bouncing models of the universe, the end of one cosmic timeline could seed the beginning of another. Time could collapse and then restart, with a new arrow pointing forward. If this is the case, then what looks like the end of time might only be the end of one version of it, with another waiting to begin. How time ends remains a great mystery in cosmology. What we do know is that time is not guaranteed. It is fragile, bound to the physics of space and energy, and woven into the fate of the cosmos itself. To think about the last tick of the universe's clock is to stretch the imagination to its limit. It is to face a possibility stranger than any emptiness, the erasure of time itself, leaving not a void, but an absence so complete that no word, no thought, no measure could capture it. The potential for quantum resurrection. Can we reignite the universe? Could quantum chance breathe life back into a cosmos that has grown cold and still? If the right kind of fluctuation occurred, it might gather enough energy to trigger a new burst of expansion, like a miniature version of the Big Bang. In such a case, a patch of space could suddenly inflate, creating an entirely new universe. Our universe would not have truly ended. It would have given birth to another through the chance workings of quantum mechanics. This idea connects to what is sometimes called eternal inflation. In this view, our universe itself may be just one bubble among many. The Big Bang might not have been the one true beginning, but only a local event, a spark inside a much larger reality. If so, then the end of our universe might not be a final wall, but only a doorway to the possibility of new universes forming. Quantum fluctuations could ensure that creation never fully stops, even if one universe fades into nothingness. But there is another stranger layer to this thought. It deals not with entire universes, but with smaller, localized events. Some physicists have speculated about what are sometimes called Boltzmann brains, self-aware structures that might randomly appear from quantum chaos. The idea is that given enough time in a universe approaching heat death, chance fluctuations might briefly form complex structures, even patterns of thought, that resemble living minds. These brains would not last long. They would dissolve almost as quickly as they appeared. But they represent a shocking possibility, that in the final silence of the universe, isolated sparks of awareness might still flicker into existence, unconnected to stars or planets or galaxies. If chance alone could create such complexity, then the resurrection of an entire universe might also be possible. It would not be resurrection in the sense of restoring what was lost. Instead, it would be something new, something born out of randomness. Just as the Big Bang may have been a sudden and unexplained release of energy, a future fluctuation might create another moment of expansion, another reset of time, another chance for creation. The difficulty is scale. At the quantum level, fluctuations are common but small. They happen all the time in the vacuum of space. What would be required is an immense fluctuation, one capable of sparking inflation and building a whole new universe. The odds of such an event are unimaginably low. But the universe has one advantage. In a cosmos that stretches on not for billions or trillions of years, but for numbers beyond human imagination, even the most unlikely events might eventually occur. A fluctuation that would seem impossible on human timescales could become inevitable when the clock runs for eternity. If such a new universe did emerge, what would it look like? Would it carry the memory of the old, or would it be entirely fresh? Most theories suggest the latter. The birth of a new universe through quantum fluctuation would erase the details of the one before. Its physical constants might be different. Its dimensions might not match ours. It might be unrecognizable, governed by strange rules. In that sense, it would not be our universe reborn, but a stranger, a new reality unfolding from the ashes of the old. There is also the question of whether such a rebirth could be observed at all. From within our universe, there may be no way to detect it. A fluctuation that creates a new bubble universe might cut itself off completely from our own. To us, the universe would still appear to end in heat death, with no visible resurrection. The new reality would blossom in isolation, hidden from any eyes that might have looked for it. If universes can be born from fluctuations, then perhaps reality as a whole is an endless chain of births and deaths. Each universe may run its course, cool and fade, only for another to spark into being somewhere in the quantum sea. This cycle could go on forever, without need for a beginning or an end. Our universe would then be just one link in an infinite story, one moment in a chain that stretches beyond time itself. This picture is comforting because it suggests that creation never truly stops. Even after our universe dies, reality itself will go on. But it is also unsettling because it suggests that our universe is not special. It may be only one of countless experiments played out by chance, with no guiding hand or ultimate purpose. The resurrection offered by quantum mechanics is not the return of what was lost. It is the endless possibility of something new, born not from design, but from randomness. Alternative endings to the universe. When people first began to think about the universe's end, the idea of a big crunch seemed natural. If the universe started with a bang, maybe it would end with a collapse. The thought was simple. Gravity pulls everything inward. If there was enough matter, enough energy, then the expansion of the universe would slow, stop, and reverse. Galaxies would drift closer, stars would gather again, and eventually everything would collapse into one final, unimaginable point of density and heat. This vision of the cosmos carried a strange symmetry, a neat circle where the end mirrored the beginning. Yet as science advanced and new observations were made, the big crunch became less certain. The universe, it seemed, might not close in on itself after all. Instead, it could follow other paths. With dark energy at work, the universe does not seem to be heading toward collapse. Instead, it is racing outward, with expansion accelerating faster and faster. If this continues, the universe might never come back together. Instead, it may face endings stranger than the neat symmetry of a crunch. One of these possible endings is called the Big Freeze. In this vision, the universe expands forever. Over unimaginable timescales, everything fades. What's left is a universe of thin radiation, scattered particles, and darkness. It does not collapse, but it does wither away into silence. The Big Freeze is not explosive or violent, but it is absolute. It represents the slow death of everything, stretched over trillions upon trillions of years. Another idea is the Big Rip, which would be a violent, all-consuming unraveling of the fabric of reality. Instead of fading into quiet darkness, the universe would end in chaos, pulled apart by its own runaway expansion. But the possibilities do not stop there. Some scientists imagine stranger cycles, where the universe might experience rebirth. In one version of this idea, dark energy itself could change over time. If it were to weaken, expansion might one day slow and reverse after all, leading to a collapse, but not into a final dead end. Instead, that collapse could ignite another Big Bang, giving rise to a new universe. This repeating pattern is sometimes called the Big Bounce. In it, universes may die and be born again endlessly, with no first beginning and no final end. Other theories imagine, instead of ending, our universe might give birth to new ones. The false vacuum idea has already been discussed, but there are also ideas that focus on the very structure of space-time. If space-time is not smooth but instead has hidden layers or dimensions, then the universe might not simply expand forever. Instead, it could one day tunnel into another state. In quantum physics, even things that seem impossible can sometimes happen through rare fluctuations. The entire universe could undergo such a change, falling into a new configuration of reality. To the beings inside, it would appear as the sudden end of everything, but on a larger scale, it could mark the beginning of something else entirely. Each of these visions carries its own kind of weight. The Big Crunch gave people a simple story of return, a comforting balance between beginning and end. But the alternatives are harder to grasp. The Big Freeze speaks of endless emptiness, a future where not even memory can survive. The Big Rip paints a picture of destruction so complete that even the smallest building blocks are torn away. The Big Bounce and related ideas offer an endless cycle, where death is never truly final. And quantum models hint at transformations beyond our ability to imagine, where the very rules of reality could shift in an instant. The search for which of these paths is most likely is ongoing. Scientists look at the motion of galaxies, the behavior of dark energy, and the deepest structure of space-time itself. But the universe guards its secrets well. The timescales are too vast, the energies too extreme for us to test directly. What we are left with are glimpses, patterns of light, faint signals, tiny shifts in the expansion rate. From these fragments, we try to piece together a story about the ultimate fate of everything. Civilizations in the far future, will they adapt or perish? For any civilization alive in the deep future, survival would mean confronting conditions beyond anything we can picture from our short-lived age. What would intelligent beings do in such a place? Would they find ways to adapt, or would they fade along with the dying cosmos? The first challenge would be energy. All life as we know it and all technology depends on sources of power. Civilizations grow and thrive because they can use the energy of their environment, whether it is fire, the burning of fossil fuels, the flow of rivers, or the nuclear fusion inside stars. But as the stars age and exhaust their fuel, the great furnaces of the universe will shut down. The night sky of a far future world would not be filled with glittering lights as ours is. Instead, it would be empty, with only a few faint embers of red dwarfs or cooling white dwarfs glowing weakly in the dark. A civilization living in that era would have to turn elsewhere for power. They might tap into black holes. For trillions of years, black holes will remain some of the most energetic objects in the universe. Matter falling into them releases vast amounts of energy, and even their slow evaporation through Hawking radiation could, in theory, be harnessed. Advanced beings could build structures to capture this energy, feeding matter into the black holes to prolong the supply. Instead of sunlight, their world might be lit by artificial systems powered by the slow death of a black hole. The thought is strange, but not impossible. Civilizations growing like parasites on the last flames of creation, clinging to the few places where energy can still be extracted. Other possibilities could involve tapping into the decay of matter itself. If protons eventually break apart, as some theories suggest, that decay would release energy. Civilizations could attempt to collect and channel the faint trickle of power from matter falling apart at the smallest scales. It would not be much, but for beings with time horizons stretching across billions of trillions of years, even the smallest energy could be carefully preserved and stretched. Their lives would become a constant struggle against dwindling fuel. an existence where patience and efficiency matter more than expansion or growth. But perhaps adaptation would not only be physical. In a universe where physical resources are scarce, civilizations might turn inward. Instead of building vast empires among the stars, they could collapse into themselves, retreating into digital or simulated worlds. If they had the technology, they could upload consciousness into machines, existing as streams of information within computers that run on as little energy as possible. Entire societies could live in worlds of thought, their civilizations continuing in forms unimaginable to us. For such beings, the outside cosmos might become irrelevant, a frozen void they no longer need to engage with. Their survival would not be about mastering the universe, but about mastering themselves. Of course, this assumes that civilizations reach such levels of technology. Many may not. If history shows anything, it is that civilizations rise and fall, often undone by their own choices, long before the environment forces them out. For beings in the deep future, the question may not just be how to survive a dying universe, but whether they can endure the challenges of their own nature. The longer a civilization exists, the more chances there are for mistakes, wars, collapses, or choices that lock them into decline. It could be that very few ever survive long enough to face the final cooling of the cosmos. And yet, some might. For those that do, the universe will not be kind. The vast distances between surviving islands of matter will grow even greater as cosmic expansion continues. Communication across the universe will become impossible, and civilizations will find themselves in deep isolation. If more than one survives, they may never know of each other's existence. Each will become the last light of its own region of space, imprisoned in solitude. Civilizations may adapt not by fighting to survive forever, but by choosing to end. Perhaps there comes a point when a people accepts the futility of holding on against the slow death of the cosmos. They could decide to end their existence on their own terms, fading away while their world still holds some energy and light. It would be a kind of surrender to the universe's fate, a recognition that no struggle can outlast entropy. Others might instead resist, fighting endlessly to stretch their survival into the coldest reaches of time, refusing to give in even as energy dwindles to almost nothing. There is also the chance that civilizations would try to rewrite the rules, maybe attempt to create new universes through quantum fluctuations, or tap into dimensions beyond our own. If any beings in the far future discover such possibilities, they might attempt to escape into a fresh cosmos, carrying their knowledge with them. In that sense, adaptation would not mean living in the dying universe, but leaving it entirely, planting seeds of civilization in newborn realities. For us, 1,000 years feels vast. For the universe, 1,000,000,000,000 years is a blink. Civilizations, if they survive that long, would measure their lives in ages beyond comprehension. To adapt in such an environment would mean planning for spans of time greater than the age of our universe today. The patience, wisdom, and resilience required would be unlike anything we can imagine. Beings of that future would think and act at a pace completely alien to us, shaped by a universe that moves slowly towards silence. Still, one wonders whether meaning itself could survive. A civilization may adapt physically, finding ways to keep energy flowing and life continuing. But in a universe growing steadily colder and darker, what purpose would drive them? Our own civilizations are bound to stories, hopes, and dreams tied to growth and exploration. In a cosmos where nothing new is possible, where the stars have all burned out, would hope itself fade? Or would civilizations find new meanings in endurance, in the simple act of persisting against the night? Perhaps survival would not mean existing forever, but existing long enough to create something lasting. Civilizations might adapt for as long as they can, and in the process leave behind traces, structures, signals, or entirely new universes that outlive them. Their legacy could be written into the fabric of reality, even if they themselves eventually fade. In that way, the struggle against the dying universe would be about leaving behind some echo that says they were once here. And on that bittersweet note, today's journey comes to an end. What other wild concepts would you like to hear about? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.